where I can't stop things.
I mean, do you want to go back to the beginning, maybe?
Yes.
Okay.
Okay, let me share screen. Oh, shit, that's not. Okay, there we go.
Hi, Dimitri.
Oh, hi. I hope you... Yeah, now, can you hear me?
Yep, we can hear you.
Oh, great.
Yeah, hi.
Well, it's just us for now.
Yeah, I'm trying to get the others. We can only invite one person at a time, and we have to wait for them to accept before we can invite the next person. It's a very bottlenecked system.
Yeah.
I'm still waiting for Bharati. Do you want to get, is Weishi the other person?
Yeah, I don't see him. But we've got people coming in. So hi, everybody. I don't see Will here either. Actually, maybe I'll put it on the schedule slide right now, just so that it's a little bit more useful. Okay, we got the link. So let me share that link with Will, and he can figure out the you know what? Let me share the file instead, just so that I can use my screen. I won't be able to point, but I think people can figure it out. Oh, I see a sushi. Should we just like bring people on the stage?
Sure. Will is having trouble getting into AirMeet.
Oh no. Were you able to invite Bharati?
Still awaiting a response from him.
Do you want me to try? Or is that going to be like a race condition?
Sure, I canceled. You can try.
Okay. Oh, invite rejected as he's on the Erlang stage.
What?
All right. All right, so, oh, I see Will. Can you invite,
Hello.
Hi.
Hi, Dimitri. Hi, Greg. Are you living in shadow today?
This is my lighting This is life now. It's too early in the morning for light.
Okay. You might want to get on that.
I don't know that it's not there isn't really a great solution.
You can turn your table around.
Yeah, I could, but
can you move the lamp?
I think it's more if I position myself correctly, then the video corrects the luminosity. Can you see me better when I'm like this?
Marginally.
Okay.
You're still basically invisible.
So, Will, do you have? Does miniKanren have Twitter?
Does miniKanren have Twitter?
No.
What is that?
So,
is there a Twitter
we have a live stream link. So I'll paste the live stream link just in case anybody has social media.
miniKanren does have a Twitter, if I can remember how to get into it.
Actually, you know what we can do? Greg, do you want to share that link in the what do you call that? The Google group? Oh, I think Greg is busy moving his lamp.
Oh, I see.
Is that any better?
Yes.
Oh, great.
Yes.
Yeah, this incremental refinement.
Yeah.
Someday we'll be able to see you.
Just have to wait for the sun to come up.
So why is the sun up here but not where you are?
You're on a higher floor.
That's maybe. Yep. So so it's technically 7. Should we get started?
I think we should, so that the speakers will have sufficient time.
Yeah. Did we ever get that link, by the way, about the live stream?
Yeah, I pasted it again in the chat. Do you want me to paste it again?
Oh, I see.
I guess.
Got it.
I can tweet this from my own personal account, which has more followers than.
Yep.
I think there's a miniKanren Twitter account. I think that tells you how active it is.
Hello.
Hi.
Hello. All right, so I just tweeted.
All right, perfect. So maybe we'll get started then. Greg, do you want to start with the official introduction, kickoff, whatever it is?
Yeah. So, hi everyone. Welcome to the 3rd miniKanren workshop held virtually in Korea. My name is Gregory Rosenblatt, and
my name is Lisa Zhang.
Yep, we're the co-chairs and organizing committee this year. So, you want to advance? So this year we have 7 papers and 2 keynotes spread across 4 sessions, punctuated by 30-minute breaks. And Lisa's going to paste the link to the program in the chat.
I forgot about this part. I don't actually.
Okay, we'll get the link soon. You want to go to the next slide anyway? I'll keep talking. So our keynotes are given by Nada Min, who will be talking about extending miniKanren in at least 2 ways, and Chris Martins, who will be talking about relational content generation. Next slide. So this year is also the first year that we have a steering committee, which makes us a real workshop now. They're seen here alongside the program committee, which worked tirelessly to review all the papers you'll see here today. We really appreciate their work. And Lisa, do you want to talk about the technical stuff?
Yeah, so since we're using a new platform this year, I thought this would be a good time to talk about what's available on AirMeet to make this workshop as interactive as it can be. So you should be able to see a chat functionality. It should be sort of somewhere in that direction. If you're here, can you please just type something in the chat. Maybe type, where you're joining us from.
Russia.
Russia.
Oh, hi, Katerina.
South Carolina.
Nice to see you here.
Hi, Evan. All right. So please. Oh, Germany. Nice. So
Nice.
please use the chat to talk to the speakers. Ooh, India. During the talk. Most of the talks are going to be pre-recorded, so expect most of the authors will be in the chat. And for more involved questions that you want the authors to discuss after the talk, there's a Q&A tab right next to the chat tab. So can somebody or multiple people maybe type a question in the chat? But before you do so, there are two options for typing a question. So if you use the silent flag, like the question on the right, will there be cake? Then that we will not invite you to the stage, like where Greg and Will and Dimitri and Bharathi are. But if you ask the question without the silent flag, then we'll bring you up to the stage to ask the question. Just again, so that there's more interactivity going on. And I should warn you that the session is live streamed. It is recorded. So in case that factors into whether you want to use a silent flag. So can we maybe get one or two questions in the Q&A, just so that we can try out this workflow, just so that you can see what it's like. So would someone like to volunteer to ask a question?
Oh, we got a question.
So I guess, Bill, you're already on stage, so I can't bring you on stage, but your question will show up here, and I guess I can remove you from stage, but I'm not gonna do that. How do live talks work? Yeah, that's great. Okay, so let me bring you onto the stage. And I think you're going to have to say yes to join the stage. Hi, Evan.
Hello, can you hear me?
Yes, we can hear you. So the way that live talks will work is that I will, or one of us, Greg and I, will invite you to the stage, and you'll be able to share screen, and we'll be able to see you, and we'll hide ourselves.
Okay.
Yep, so thank you for the questions. So then I will remove you from the stage and mark this question as answered. There is also, go ahead.
I was just going to mention yesterday when preparing for the Scheme workshop, a speaker mentioned that they would actually prefer to have some friendly faces visible, so that they don't feel like they're talking to a wall. So if someone would prefer to have people have us visible, please let us know, and we can, I guess, keep our cameras on.
Yeah, we can bring other people on the stage as well.
Yeah.
It's a great point. So there is a lounge area that we can go to during the breaks. You can get there by finding the lounge button that's somewhere up there. Please don't go right now. But there are two miniKanren tables, miniKanren 1 and 2. So I think each table has a maximum capacity of 50 people. So we might be able to have everybody fit in miniKanren 1. So maybe we should just use miniKanren 1 unless it's full. And there'll be an automatic alert when the next session starts. And again, this is the schedule. Are there any other questions before we get started with our first talk?
All right, how about we just get started?
Yeah, let's do that. So let me find the video. So if ever we're slow, it's because we're trying to find things on AirMeet. So there we are. So our first talk is by, actually, can I hand it off to Will Bird, who is going to be our session chair today. So I'm actually going to maybe remove people from the stage. Oops, I don't want to. And yeah, and then Will, you have the floor.
Thank you, Lisa and Greg. I'm excited to be here for the third annual miniKanren workshop. And one of the things that's kept miniKanren going and this workshop going is the great work that's come out of St. Petersburg State University and JetBrains research in Russia. And we're going to hear about some very interesting work on studying complexity of the interleaving search, which is sort of one of the special sauces that makes miniKanren work well for things like program synthesis. So we're going to hear from Dmitry Rozplotkas, and also, of course, he's working with Dmitry Buchilov, who runs this program at JetBrains in St. Petersburg and is a great friend. All right, please take it, Dmitry.
I will present the first developments of our ongoing project aimed at providing a formal model for complexity of programs in miniKanren. For now, there is no such model, and when analyzing performance, a programmer is usually relies on time measuring for specific instances. This way, we have to guide program design by some known examples and heuristics, rather than general understanding of the search. So the examples with surprising behavior will arise from time to time. Let's consider the following example comparing two definitions of the relation computing the length of a list. Naively, we can define it as this way, just taking an imperative definition and transforming it step by step into the relational form. But to get this conventional definition, we have to move the recursive call to the end. This way, we will execute all the constraints before the recursive call, and the program will be suitable to be run backward. But let's measure time for inputs of different sizes if we use this relation as a function to compute length. You can see that the naive version is significantly slower, although it performs adequate steps in an adequate order. The difference is even more striking if we disable a curse check in unifications. In this case, the dependency for the naive versions seems to be linear, while for conventional version, it's obviously not non-linear. If we look closer at the unifications performed, we will see that there is no reason for this difference, and the reason is somewhere else. In this project, we want to build a formal model to be able to understand such behaviors and be able to predict them. This model should include different parts of the search. Abstractly, search in miniKanren can be decomposed into the following three parts. Scheduling, that transforms relational execution into a sequence of unifications. Performing the unifications, that involves occurs checks by default, and verification of the answers at the end. So the overall time can be decomposed in these four components, and it's actually the component of scheduling time that is responsible for the difference for the length example. Notice that we separate time of occurs check because, as we've seen in the previous slide, it can make a huge difference. So we want to be able to detect it. Our goal is to construct a model that provides formal characteristics for all these components of time and can be applied to estimate their complexity for a given program. We have to choose some version of miniKanren as a basis. So we are focusing on the conventional or on the canonical version that is described in the book Reasoning Schema. The Reasoning Schema. For now, we have a model, but it's only can be used to estimate the time of the full search when we're asking for all the answers, and for a limited class of programs, including many practically interesting ones. The rest of the talk is structured as follows. First, we will discuss methods to estimate time for different parts of the search separately. Then I will informally describe a technique that brings these methods together to estimate complexity of a given relational program using symbolic execution. And finally, I will present results of evaluation of our approach for some known examples and some observations on these results. Let's start with analysis of scheduling time. To analyze the behavior of the search, we rely on an existing operational semantics for the interleaving search. It's a deterministic label transition system with partially evaluated search trees as states. Leaves are goals we need to execute, and nodes correspond to M+ and bind. Evaluation is of the relational program is defined by the path along the transition in this transition system that is called trace. As a first approximation of the scheduling time, it's natural to take the number of transitions in the trace, which corresponds to the number of forcings when traversing a lazy stream. However, each of these transitions does not necessarily take a constant time. Actually, each of these steps involves navigation to the leftmost leaf to find a goal to execute. So, a better approximation of scheduling time is a sum of depths of the leftmost branch for every state in the trace. We derive recursive formulae for this value that we call the scheduling factor for M+ states and bind states. And the exact equations, recursive equations, are rather cumbersome to use directly, and we also have some approximations that are convenient to use. It's worth noting that to use formulae for bind states, we need to know all answers produced by the search for a substate. We will use this recursive formulae to estimate scheduling time in the future. Now let's move on to analysis of unification and reification time. In general, exponential in the worst case. But the majority of instances that we meet in logic programming are simple and can be solved quickly, even by the simplest unification algorithm. For this reason, sometimes in logic programming, unifications are regarded as basic operations that take constant time. We want to have this advantage too, but also we want to describe our model more rigorously. So we formulate two dynamic criteria for execution of programs that ensures that unifications are simple, and we consider only the programs that satisfy these criteria. We consider the Robinson's unification algorithm with triangle substitution that is conventional for miniKanren, and estimate time of a curse check separately. Both unification and reification performs some basic operations on substitutions. And first we need to determine the time of these operations. Time of lookup and add depend on the data structure we use to represent substitution. Different implementations of miniKanren uses different data structures, but in all practically applicable ones that we know of, lookup and add have logarithmic complexity or less. So we can, and as we expect complexity of relational programs to be polynomial or even bigger, we can regard these operations as basic and actually count the number of them to estimate unification time. Another basic operations that is specific to triangle substitutions is walk, that finds the value for a variable in the substitution. To do it, it may need to go through a chain of variable-to-variable bindings. So in the worst case, its complexity is linear on the time or on the size of the substitution. But in our experience, the variable-to-variable bindings are quite rare in practice. So as a first criterion, we impose the absence of such bindings during the evaluation. Under this condition, the number of under this condition, walk takes a constant number of lookups. The Robinson's unification algorithm is a simple recursive descent on terms unless some variables are updated during the process by bindings that are found by the bindings that unification adds to the substitution. Again, we suspect that this situation is not so usual in relational programming. So as a second criterion, we require that all unifications during the evaluation are linear, meaning that every variable occurs in the terms at most once. Under this condition, the recursive descent only goes to the closest variable, so the number of basic operations it requires is bounded by minimum of sizes of terms. If we then perform a curse checks, we need to go through the rest of the terms. So minimum in the estimation changes to maximum. And the reification simply goes through all terms for all answers at the end. So the number of basic operations it requires is proportional to the total size of all answers. Now that we discussed methods to estimate different parts, the time that different parts of the search takes in general, let's move on to a technique that brings them together to estimate a complexity of a given relational program. But first we need to state the problem formally. Complexity is a function that depends on some parameters of the input. And to denote these parameters, we use symbolic variables. Symbolic variable can be regarded as some ground term which represents an object from some meta theory depending on the relation. It can be a number, a graph, a string, or anything else. And then we ask a question of this, a question like this: how much time, depending on the list L, does the different parts of the search take for the following query, where we specify the first argument with the representation of this list L for length relation, and ask for the second argument. We then can calculate complexity within the meta theory, and the answer can contain notions from the meta theory too. For example, complexity of scheduling time depends on length of a list. The technique we propose contains the following stages. First, we run the body of the relation symbolically and construct so-called symbolic scheme, which explicitly shows all the information that the methods of estimation described before require. We then check the criteria for simple unifications on this scheme, and if they are satisfied, extract the recursive inequalities for the all components of the time of the search, using the estimation that we described before. Then we can solve these inequalities within the meta theory to derive the complexity of a given program. Let's take a brief look at the specific example that analyzes of how we would analyze this query, computing the length of a list using naive relation. The symbolic scheme corresponds directly to the body of the relation, but it also shows all the answers that are transmitted through the search in forms of bindings that are produced by sub-goals. And it also shows the values of all the terms at the point that they are evaluated. We can then, on the scheme, we can easily check the criterions and go through the scheme to applying our estimations directly to extract recursive inequalities for different components of the search. For example, for time of unification without recursive checks, we extract the following inequality. It can look rather complicated, but if we consider two cases when a list is empty or not, we get these two simple inequalities from which it is evident that the complexity of unification is linear on the length of the list up to a logarithmic factor. The detailed description of how the process of constructing scheme and extracting inequalities works can be found in the paper. And for now, the technique that we described has a number of limitations. First, we only have informal descriptions, so we can't automate any part of the process. Second, we need an oracle that will tell us the answers for internal relational calls. So before analyzing the time of the complexity relational programs, we need to know which answers are produced by the search. And also, as I mentioned before, we can only analyze the full search and only a certain class of programs that satisfy criteria for simple unifications. We applied our approach for a number of known examples. Specifically, we took relations for operations on numbers and lists and ran them in different directions. All these examples satisfy requirements for our technique, so we were able to get complexities, and in all cases they are polynomial. Here are just some of the results. The full table you can find in the paper. From looking at these results, we take these two observations. First, occurs check are really to take a huge role in the overall time. In all cases, the complexity of this component dominated all others, and in most cases, the presence of occurs checks increments the degree of the polynomial for the overall time. And the second observation is that position of the recursive call makes a huge difference for scheduling time. And because of it, we can see some surprising behavior, like the fact that sometimes running relation backward is faster than running it forward as is intended. For sanity check, we performed some actual time measuring for these examples for an exemplary implementation of miniKanren. We got graphs like this one for overall time, depending on each parameter for each query. It's hard to get a specific character of dependency from these graphs, especially because the precision we are able to achieve is rather limited. But after studying them in detail, we haven't found any example that violates our predictions. This work is still in progress, but we have already got some results and interesting thoughts, and here are a few of them. First, we can use help. First, a formal model for time complexity can help us to understand some strange behavior of relational programs and may guide program design and language implementation. Second, symbolic execution can be handy to calculate some characteristics for recursive relational programs which depend on parameters in the input. And finally, complexity study confirms some common wisdom for miniKanren programming, like the fact that that occurs checks are expensive and you should omit them if possible, and that sometimes placing recursive call in the end can make things better. That's all. Thank you. Will, we can hear you, Will. I'm afraid.
Yes, thank you. Thank you, Dmitry. Thank you. Thank you very much. All right, well, it's very, very interesting. So we have symbolic execution techniques being applied to miniKanren. Okay, so for anyone who has questions, there's a Q&A tab on the right. And if you ask a question, we can put that up on the screen, and also we can invite you up to ask the question if you'd like. And so I've got a couple of questions while we wait to see if there are questions from the audience. One question I have is that now that you have the symbolic execution infrastructure in place, are there any other properties that you would like to use symbolic execution for besides computational complexity of relations?
Yeah, it's interesting to look for some other applications, I guess. But we designed this, we like developed it specifically for this application. So I haven't really thought yet how it can be applied. Although surely, like symbolic execution is powerful to do something. I don't know. It's not totally developed yet. So we are just still in progress. So I guess we are trying to figure out what we can do first with symbolic execution, and then we will see for some other application. But I don't know. Maybe if somebody has some other applications, it will be interesting to hear. So there should be, of course.
Another question I have is in Chow Prolog. The Chow Prolog can do automatic parallelization of logic programs, where the user puts annotations on the relations to say what the computational complexity is, and then using a built-in cost model, the compiler will try to automatically parallelize the logic programs and gives you a guarantee that your programs will not run slower according to the cost model when it's parallelized. It won't run faster necessarily, but won't run slower. I was wondering if maybe these techniques that you've been developing could be used and applied to automatic parallelization of miniKanren programs or OKanren programs.
Yeah, I would need to think about it, I guess. It's an interesting, somewhat different approach, I guess. Maybe it can be combined in some way. We can use it, I guess, in other direction. If we have take this idea of having annotated complexities, we can use it for our approach, I guess, to use inequalities to get maybe better approximation, or if we to get easier. But yeah, if we instead of annotations, we can use our predicted complexities. But for now, as I said, it's all manual, so and it's really not trivial to get it automated. So maybe if we have with some kind of annotations, we can make it more automated. But
Well, and I see a question here from Lisa, which I will. Oh, great. Lisa will put it on screen. Are there any strategies to remove or reduce a curse check from unification?
Yeah, it's a question that is interesting for us for us too. So it's in our work, we kind of provide motivation and really urge to get these methods to get rid of curse checks. Maybe you can say something about that, but some methods that we have in mind, we can use some static checks to check that there will be no need for curse checks, that will be no variables, circularity. So there are methods in Prolog. We can just, I guess, apply it to Karen. But maybe you should know more about it than I do. So,
well, one thing I know is that Jason Heeman and a student, I believe at Northeastern, are currently working on a miniKanren compiler, and I believe that's one of the optimizations that they're working on. And I think also I've been working with Nada Min and Michael Ballantyne on staged evaluation, and so that maybe that would be something we could do as well. But it's surprising how expensive it seems to be. You know,
it was for us too.
Yeah, that was pretty surprising.
Yeah, maybe there are some difference. So it's only for the naive, the most basic implementation of curse checks, but I guess in basic miniKanren implementation it's really the case that they are very, very expensive. Maybe some better versions for curse checks is possible too. So I know.
What about for like something like faster miniKanren? Is there a way without sort of doing the staging? If that makes sense as a question.
I don't know.
To avoid the curse check, you mean?
Yeah, or figure out what to do without having like a huge change to.
That's a good question. I'm not sure. You know, the original version of miniKanren didn't have the occurs check by default. You had to use a special version of equal check because of this, and then we decided that wasn't safe enough, and so just okay, we'll commit to being safe all the time, but we may have been paying more than we thought. And the other thing I thought was interesting is your dynamic criterion number 1 was based on this observation that you almost never unify a variable with a variable, which also surprised me. I thought that would happen quite a bit.
Well, it's just some, I guess, I'm not can give you any guarantees. It's just the feeling that we have from our number of examples that we have tried, and it didn't happen there. Maybe in some other, like if you do maybe like synthesis of programs, maybe it's happened there all the time, and we just haven't looked into it yet. So. Don't take it as a guarantee. It's just what we think.
Thank you.
I see Michael Ballantyne on the stage also. Is that to talk about the first check, maybe?
So Michael said something in the chat, and Evan said something in the chat as well. So I'll just bring them both on the stage.
Okay.
I was just noting that to do the occurs check removal, it's kind of hard to do with a implementation of miniKanren based on a embedding like we usually do, because you need just a little bit at least of non-local static analysis. So you can see, for example, that one of the variables involved has just been fetched, so you know that it can't possibly occur in something, for example. So that's hard to do in the embedded version.
I wasn't really expecting to say more from this, in addition to this comment, but I was just remarking that something about what you just described in terms of rarely unifying variables and variables had some kind of analog in a piece of code that I realized was never being used, that I prepared for variable unification, and so I needed more time to think about exactly why that is happening. But it was a program synthesis task, so maybe there's something interesting there, but I have to think about it.
I guess in some sense it maybe isn't surprising, because normally you're going to unify a logic variable if something has structure. But I guess I'm surprised that if you're really almost never unifying a variable with variable, then maybe there's some way to take advantage of that.
Yeah, we'll have examples where we do it, so it's not never happening, but it's just in normal execution that does not, in our experience.
Sorry, I missed something that I wanted to catch. So why is the fact that you don't often unify a variable with a variable important?
Because walk depends on how many. Well, if it's just in the worst case, if you have many, you can go through the chain of it in walk, and it makes complexity bigger.
Right. Okay.
Okay. Well, I think time-wise, we should probably move on to our next talk. Thank you very much. Virtual applause, real applause. That's very interesting. I'm curious to see how far you can push this. Thank you very much.
Right, let me just find the next.
Greeting.
All right. Well, let's see. The next paper is going to be by Bharath Joshi and myself. Hello. I think you're muted right now.
Oh, hello.
Hello. I mean, I guess I can introduce you. It's a little odd because I've been working with you for a while. Do you want to say anything about how we started working together?
Yeah, so the way we met was through the SIGPlan mentoring initiative, and then I was Will was recommending me things to read. So we were hacking on dependent types first, normalization by evaluation, trying to implement that in miniKanren. And then I started going through reasoned schema, and then I got interested in miniKanren. So I asked Will if there were any ideas that we could hack on together, and he said, well, we can do miniKanren, and that's how we started doing this.
That's right. So this is on miniKanren, and this is also kind of at a meta level, an example of the mentoring program set up by ICFP and run by Talia, which is I found to be very enjoyable. So thank you very much. And so we're going to learn about miniKanren. And Lisa, do you want to go ahead or Greg, do you want to go ahead and start the video?
I am Bharat, and I will be presenting our paper miniKanren towards a relational metacircular interpreter. Firstly, I would like to motivate our problem. So on one hand, we have relational programming, which is all about expressing computer programs as mathematical relations. On top of this, we have relational interpreters, which are interpreters for programming languages written in the relational programming paradigm. These have been used to solve several interesting problems. For example, there's Barleman, the relational scheme interpreter, which has been used to do things such as coin generation and turning proof checkers into theorem provers. On the other hand, we have metacircular interpreters, which are interpreters where the interpreted language is same as the interpreting language, reducing the meaning of all possible programs to the meaning of one particular program, the metacircular interpreter. Thus, we unify these two fascinating ideas and ask if we can have a metacircular relational interpreter. One natural way to go about implementing metacircular interpreters is to simply syntactically translate every expression in the interpreted language to a corresponding expression in the interpreting language. Such a translation is called a shallow embedding. So, let's take a look at a shallow relational interpreter for a tiny relational language to understand its shortcomings. The language we look at is quite minimal. All it has is unification, fresh so that we can introduce new logic variables, conjunction and disjunction. The only arguments allowed in a unification are logic variables or quoted datum. Although this language is quite minimal, for example, it does not have numbers or cons pairs, it is still useful to understand the limits of expressivity of a shallow interpreter. Let's see how we would go about writing a shallow interpreter for this tiny relational language. Our interpreter is the two-argument relation eval programo between the program and the output of the program. The program is a run1 expression with a query logic variable, which is a symbol, and a goal expression. To evaluate the program, we evaluate the goal expression of the program by creating an environment where we map the query logic variable to the output logic variable. This is how we will be using environments throughout the interpreter. That is, we will use the environment to map source logic variables to host logic variables. Let's see how we evaluate goal expressions. To evaluate a goal expression, we first look at the kind of goal expression it is. If it is a unification, we translate it into a host unification by having both the term expressions E1 and E2 here evaluate the same term t. To evaluate a fresh expression, we extend the environment by mapping the source fresh logic variable to a host fresh logic variable. Here x is being mapped to x1, and then recursively evaluating the goal expression in the fresh. A conjunction is translated into a host conjunction, and disjunction is translated into a host disjunction, which is condi here. Term evaluation is also quite simple. We have symbols which are self-evaluating, and then we have logic variables which are simply looked up in the environment. Lookup is pretty much what you would expect because we use association lists for environments. We first check if the car of the first element is what we are looking for. If it is, we unify the value with the CUDR Otherwise, we recursively search through rest of the association list. Now that we have walked through the shallow interpreter, let's see it in action by looking at a few examples. First, let's look at a fairly straightforward unification. The inner run query unifies the inner query logic variable with the symbol cat, and the outer query variable is the output argument to the shallow interpreter. As expected, we get back cat as the only possible answer for this query. Now let's try to perform program synthesis by providing the expected output as cat and replacing a part of the program with the logic variable x. Here, in addition to what one might expect, which is the symbol cat, we also get back another answer, which is the symbol z, the inner query logic variable. To understand why this is the case, it is useful to replace x with z and run the query forwards. Here, miniKanren tells us that the outer query logic variable x is fresh. What this means is that when we have a unification of an inner query logic variable with itself, the output is allowed to be anything, because anything always unifies with itself. This is because the way we have implemented the shallow interpreter, z gets unified with the output, which is cat in this case, and then equal z is translated to equal cat, which succeeds. Now, with that in mind, let's look at a slightly more complicated synthesis query. Here, let us try to synthesize the branches of a disjunction by providing the expected output as cat. The first two answers are explained by the previous behavior. We have an inner query logic variable. We have an inner logic variable being unified with itself, letting the output be anything. The next two answers are more interesting. They tell us that if one of the branches unifies the inner query logic variable z with cat, the other branch can be anything. This demonstrates an important limitation on the expressivity. With the shallow interpreter, we cannot express negative examples. What I mean by that is we can say what one of the answers should be. For example, here we say that one of the answers should be cat, but we cannot say what all possible answers are. To say what all possible answers are, we need to have run star queries, because that's how run star is defined. It finds all possible answers for the given constraints. But we cannot implement run star in a shallow interpreter, because to collect all answers, we would want the interpreter to express which goals succeed and which goals fail. If we try to do this with a syntactic translation, we would have to express which goals succeed and which goals fail in the host language, which is miniKanren. This goes against the relational nature of the interpreter. But if we don't rely on a simple syntactic translation and instead have an explicit representation for the goals in the source language, then we can express which goals succeed and which goals fail as conditions on this representation. Such an implementation where we have explicit representation for the source language is called a deep embedding. The key takeaway here is that we cannot implement run star semantics with a shallow embedding. And this is where metaKanren comes into the picture. It is a microKanren-like language for which we have implemented a deep relational interpreter. Now, I'd like to show some example programs in metaKanren, but before that, there are a few syntactical differences between metaKanren and microKanren that I'd like to go over. The way I'll be going over the syntactic differences is I'll take a valid micro-Kanren program and massage it into a meta-Kanren program by making one change at a time. The program that I'll be using is 5s and 6s, which is a simple one argument relation which unifies its argument with 5 or 6 and then recursively calls itself. So what we end up with is an alternating stream of 5s and 6s. The first change we make is based on the fact that miniKanren does not have Arabic numeral arithmetic. And this is important because we use Arabic numerals in the counter that we provide to run. For instance, here we provide 3. Because miniKanren does not have Arabic numerals, we use an alternative representation, what we call piano numerals. Here we represent 0 by the empty list and the successor of n as n wrapped in a singleton list. For example, because 0 is the empty list, 1 would be 0 wrapped in the empty list, wrapped in a singleton list, 2 would be 1 wrapped in a singleton list, and so on. Thus, the first change we make is we replace 3 on the first line with the piano numeral 3. Now, the second change is based on the fact that letrec is used to create the user-defined relation 5s and 6s, and procedure application is used to call 5s and 6s. Because micro-Kanren is embedded in scheme, this works fine. However, we want meta-Kanren to run in miniKanren, which does not have letrec or procedure application. So what we do is we extend the source language with letrec rel to create recursive relations and call rel to call a user-defined relation. Finally, we are still using lambdas here to delay computation. Once again, because miniKanren does not have lambdas, we introduce another construct into the source language, delay, which is used to delay goal evaluation. In summary, the 3 changes we made were piano numerals for the run counter, letrec rel, and call rel, and delay. Now let's look at some meta-Kanren examples. The first example that we'll be looking at is the usual 3-argument appendo defined in meta-Kanren. It concatenates the lists L1 and L2 into the list L. Here we call it by providing it the lists 1, 2 and 3, 4, and we run it forwards. Thus, the expected output here is the list 1, 2, 3, 4. Let's run it to make sure that is indeed what we get. And as expected, we get 1, 2, 3, 4. It must be noted that it is wrapped in an extra list because meta-Kanren itself runs in miniKanren. Now let's run it backwards by providing what the expected output is and replacing a part of the program with a logic variable. Here we have replaced this conjunction with the logic variable x, and we have provided the expected output. Let's run it to see what we get. Also, it must be noted that we use run star for the inner query, which was not possible with a shallow interpreter. As expected, meta-Kanren correctly synthesizes the fragment to be a conjunction, to be conj. Now, let us go back to the motivating example where we had claimed that having a run star is more useful than run one when it comes to program synthesis. Here, instead of run star, let's see what happens if we provide a run one and try to again synthesize X. This time, in addition to conj, we also get back dist. Notice that when we had run it with a run star, we had only gotten back conj. This is precisely the expressivity that a run star in the source language brings to the table. Now, there's a technique I'd like to present which we have found to be useful when it comes to program synthesis. I think this technique is novel in the sense that it would not be applicable if we were doing program synthesis with the relational scheme interpreter because of the difference in the nature of the source languages. That is, scheme is functional, whereas miniKanren is relational. Let's look at the technique. Here we have a simple one argument user defined relation 50 which unifies its argument with the Arabic numeral 5. We can call this relation using call rel and then get 5. Now let's see what happens if we try to perform program synthesis by providing it the expected output and inserting logic variables into the program. Here we have put in E1 and E2 instead of 5 and F, and provided the expected output as 5. It must be noted that reification of answers also uses piano numerals, so instead of _0 you have underscore the piano numeral 0. Let's see what miniKanren synthesizes for E1 and E2. Here it synthesizes miniKanren tells us that E1 and E2 can be anything as long as numbers. This may seem confusing, however, this answer is in fact correct because what's happening here is the logic variable z remains fresh. In other words, it is sufficient for 50 to succeed without having to do anything with its argument f. In fact, if we asked for more answers, we would eventually get back what we expect, which is 5 and f. If we asked for 4 answers instead of 1 answer, we would get back 5 and f at some point. Here, the first 2 answers are spurious, and then we have 5 and f. The way to get around this is by grounding the logic variable externally. That is, instead of 5, we put in z here, and then instead of having z fresh, we say we have 5 here. We call this external grounding. When we run this, we don't get spurious answers anymore. Instead, we get 5 and f. Finally, I'd like to touch upon the limitations of the current interpreter. Firstly, it's quite slow because we don't do any optimizations. The goal with the work so far has been to have more expressivity. Some techniques we'd like to explore to improve the performance are partial evaluation to overcome the interpretive overhead, use techniques from Parliament, and also guiding the search. On the other hand, we would also want miniKanren to be metacircular. Currently, miniKanren does not implement disequality, absento, and data type constraints. Furthermore, LitRec-rel does not support mutually recursive user-defined relations. Finally, it would be useful to have a relational parser for things like condy, as currently everything must be written using dist and conj, which makes the programs quite verbose. That's it for my talk. Hope everyone enjoyed it. Questions and feedback are welcome. If you would like to access any of the code, it's available on my GitHub repository. You can also Google search for miniKanren, and I believe the repository comes up.
Greg, are you going to help with the questions?
Yes, I am.
Feels
I
a little
have
weird because I could ask myself questions about the paper, but that's strange.
Yeah, so I guess the first thing I'm curious about is you mentioned using techniques from Parliament. What techniques would those be?
Well, I haven't looked at them yet, but from what I know,
Okay.
some techniques from Mercury have been adopted.
Okay. Something I was wondering, I noticed you designed it so that you put letrec_rel nested inside of the run. Can you explain why you chose that rather than putting it on the outside of the run?
Well, it's because if you have it outside of the run, then you can't create. You're restricted to creating relation. We wanted to be able to create relations anywhere in the program. So.
Right. So what I mean is, it's nested inside of the miniKanren run. So in normal miniKanren, your definitions appear on the outside of the run, right? So you have recursive relations that can be applied in any query, in any use of run. But if you nest them inside of run, it seems more awkward to be able to access the same definitions in multiple runs.
Oh, okay.
Does that make sense?
Yeah.
So was there a design reason why you chose to put it inside, or was it just an arbitrary choice?
I think it was just an arbitrary choice.
Okay, sure. One other thing, since it is inside the run, do those relations have, do they close over the query variables?
You mean the inner query variables, right?
Right. So you have the run, you have some query variables, and then you have letrec_rel. Can those relations reference the query variables without them being passed as parameters?
Yes, they can. They can.
Okay. Yeah, I guess that's unusual in normal miniKanren too, but that's interesting.
Well, there's nothing. I mean, maybe it's an unusual idiom, but certainly it's allowed, right?
Yeah, it's allowed, but
if you believe in lexical scope, sure, have at it. But you think that maybe having letrec_rels outside of run would be closer to the normal miniKanren semantics?
I do, and it would also allow you to potentially run multiple queries with the same set of definitions, which may help in certain synthesis tasks. So, for instance, what if you wanted to express a query that describes negative information? So a query where you say, this query should return 0 answers, but you also want to describe positive information, such as this query should have these answers. So you can't really mix them in the same run. Otherwise, because you can't simultaneously ask for answers and also ask for no answers, right? Does that make sense?
I think we actually can express that through variable sharing, but it's less convenient and maybe less efficient.
Right.
So I think it'd be worth trying to do it the other way that you suggested. See what the trade-offs are.
Right. You can certainly do it through variable sharing. It's just slightly more awkward.
Yeah, definitely. I think there's a question in the Q&A. Would changing existing code to miniKanren change performance?
Yeah, Alexander, I'll bring you up to the stage so you can talk about this.
Oh yeah, so I was just curious if there would be a change if you just translated existing code to miniKanren.
Yeah, I think it would make it slower because faster miniKanren does lots of optimizations.
However, I mentioned earlier that Nada, Men, and Michael Ballantyne and I have been playing around with staging, doing staged evaluation for the scheme interpreter, relational scheme interpreter in miniKanren. And I hope that some of those techniques could be applied to a miniKanren or a microKanren in miniKanren. So if you could apply staging to that, we could probably remove one level of interpretive overhead and maybe reclaim most of the performance that we lose through the extra level of interpretation. I'm not sure if that's possible or not, but that's basically a research topic.
Cool.
Thank you. And I think Lisa maybe had a. Did you have a question, Lisa?
You're muted.
Oh, sorry. I'm actually trying to help Gracie right now to get on air.
Okay.
So I'll
Okay.
follow up with you later about my question.
Okay.
Okay. All right. Well, I guess that means we've got another couple minutes.
Actually, I think we're a little bit behind on time. So
Okay.
we'll actually.
Are you ready? Are you actually ready to play the next video then?
So let's do that. Wacy is having trouble getting on AirMeet, but I think
Okay.
Dan's
I see
here.
Dan's in already.
Yeah. So Greg, do you want to bring Dan on the screen while I find the video?
All right. Well, thank you, Brad. Thank you very much. And that sounds like an awesome paper. I'm sure everyone needs to read it. Thank you.
Hi,
Greg, do you want to bring Dan on stage?
I'm inviting him. I'm still awaiting a response.
All right,
Okay.
Dan, click on the accept button.
All right, I'll play the video.
Sure.
I'm Weishi. I'm gonna present a higher order unification algorithm that I have been working on with Dan Friedman, and this is designed for miniKanren. miniKanren was presented at a miniKanren workshop last year. It extends miniKanren with two things. One is higher order unification. The equal operator can recognize alpha, beta, and eta equivalents. The other is miniKanren has a more expressive underlying logic called hereditary hierarchy formulas. Basically, you can put implication and for all quantification in the goal position. And here we're gonna share more findings that we have made recently about the unification algorithm. So in short, with higher order unification, we can have more formulas unified with this equal operator like alpha and beta. And this beta conversion is quite subtle and powerful. So it's not surprising that full higher order unification is undecidable. But fortunately, Miller has identified a fragment of higher order unification, and people call it a pattern unification. So the idea is for the application form, if the head of this application is a unification variable, then all its arguments have to be distinct lambda variables. With such a restriction, and people often call it the pattern restriction, the term of unification looks like this. So basically, the application form is split into two forms. If the head of the application is a unification variable, then all the inputs have to be lambda variables, or here we call names. Otherwise, if it's a lambda variable being its head, then there's no such restriction. So usually people call this variable head a flex term. in a sense that it is flexible. It can be removed by a substitution. If imagine you have a substitution that maps f to some other lambda, then you can remove some variables in this a bar. And if we have a lambda variable as its head, then we call it a rigid application because you cannot remove anything by applying any substitution to it. Okay, so we can run some programs, miniKanren programs, like deciding alpha equivalence. Like here, we have lambda AA versus lambda BB, and they are alpha equivalent. So this query succeeds, and we do not need to instantiate x with anything. So x is just _0. As newcomers to this higher order unification, we might try something more interesting. For example, we can replace the first occurrence of A with a unification variable. Say, if we put x here, how can we make it succeed? Well, the answer is you cannot. This is a little bit surprising given the last example succeeds, because intuitively we would think, well, we can associate x with A and it should just work. So that was my first impression too. So, and I was really shocked that it didn't work. So I looked into the unification algorithm and it looks like this. So this is a variation of Miller's algorithm. And this is like a Nipkow and Prihofer functional version of higher order unification. So these are all the rewriting rules of this pattern unification. And you can see we can unify a lambda with another lambda called the binder-binder rule. We can unify two flex variables when they have the same head or they have different head. We can unify a flex versus a rigid. We can versus two rigids when they have the same head. So that's all good. But something is missing. Like if we think about the case just failed, we are missing a rule that is commonly seen in first order unification, which is, well, how about a variable directly unified with another term? This was not in the original rules of higher order unification. So simply, it cannot handle such a case. And in first order unification, this case is pretty straightforward, right? Because we can just do a occurrence check to see if f occurs in T. If it does not, then we can extend our substitution, saying, well, f now maps to T. So the first thing we can do is to add a new rule called maybe a var term that unifies a var and a term. And with this rule added, we can run the failed example and expect something different. Well, but it's still the same. And okay, so why is that? And it turns out to be missing this var term is part of the problem, but it's not the root. The root is there's something called the scope restriction. In the sense of higher order unification, we have to think about variable capturing. And variable capturing is handled by these scope restrictions in higher order unification. The idea is all the unification variables are considered existentially bound, and all the lambda variables are considered to be universally bound. So if a unification variable can be instantiated by a lambda variable, then this for all bound variable must occur earlier than this existentially quantified variable. That's quite a mouthful, but in brief, if this lambda A occurs later than this X, then A cannot instantiate X. So why is that? If we think about another example, it may be a little bit clearer. If we think about we have lambda AX, lambda BB, unify them, and then another pair unifying lambda CX and lambda DD. So in this case, we cannot instantiate X with A, and we cannot instantiate X with C. Neither of them works. So that's the variable capturing problem. For X, A, and C, they are both free variables, and you can just not use free variables in a substitution. So this looks a little bit strange from the perspective of, first order unification, because if you think about our first example, the alpha equivalence, it works, and suddenly then it stops working. And to get away from it, one thing we can do is to treat these lambda variables not as lambda variables, but as constants. So the Brown levels comes to the rescue. If we treat all the lambda variables as the Brown levels, for instance, in this case, lambda AX, we can instantiate X with the Brown number 0. And for the other case, if we instantiate X with 0, then it also works. So we think this is going to generate more intuitive answers, and because it's closer to first order unification. So that's just step number 1, and we cannot use the Brown numbers as a drop-in solution. We will get back to this mystery later, but for now, let's just switch gear a little bit and look at a similar but different problem. That is how alpha equivalence is handled in higher order unification. So if we zoom in into the rules, this rewriting rules, and just focus on the rule of binder-binder. And traditionally, in most, actually in all literatures on higher order unification, and this binder-binder is handled in this way, and we call it binder merging. So when we are unifying some lambda X S versus lambda YT, we just recursively unify their corresponding subparts S and T with renaming every Y in T to X. So that looks straightforward, and actually it's pretty convenient because now we do not have any alpha equivalence problems. Any alpha equivalence variables will just be syntactical equivalent. This works for most cases, but not with variable shadowing. So so that's binder merging. Imagine you have lambda A, lambda B, A apply on D versus lambda C, lambda D, C apply on D. Then binder merging is going to convert the first term to lambda C, lambda D, C versus D. This is fine. Now let's look at an example where name shadowing occurs. So what if we have a name shadowing in the first binder? If we have lambda AX versus lambda C, lambda DC, then by binder merging, then we will have lambda CDX versus CDC. Then it's kind of obvious that we should instantiate X with C or the Brown level 0. So in this case, either you are using the Brown numbers or binder merging, it doesn't really matter. You will end up with a similar result. So here we know X could be 0, but what if we install this 0 back to X and then reify all the names? Then if we go back to the original term, imagine we have lambda AAX, we will have this lambda AAA is equal to lambda CDC. So if our reifier is not carefully designed to recognize such name shadowing problems, we will generate false positives. We may also generate false positives if we are not careful enough, but another direction. So if we have name shadowing in the other term, so in the term that initiates the binder merging, then we have another kind of false positive. Imagine this. the first term will be converted to lambda C, C applied to C. Then these two terms will be unified again. So our solution to solve this problem is to not use binary merging, but use a new way to decide alpha equivalence between names. And we call this static closures. A static closure is just a variable paired with a scope, and the scope is just a list of names. And in addition, we are extending the definition of terms with the Brown levels, because we want to instantiate sometimes instantiate variables with the Brown levels. So this static closure, it should support two operations. One we call this extend. If you have a static closure phi and you have some new variable a, then extend is going to add this a to phi. And if this a has been previously added, then we are having a name shadowing. So this a should shadow the previous one, and the Brown level of the previous one should be not accessible anymore. And that's about extending, and we can use this static closure. So if we have a scope and a variable, then we can check what is the Brown level. If we have a scope and a Brown level, then we can check whether the Brown level is actually shadowed. Let's see some examples. So here's the simple case. If we have lambda A, lambda BX versus lambda C, lambda DC, we first convert them to static closures, ABX and the CDC. And for the right-hand side, it's straightforward. So we have a static closure whose term is just a name, and we can convert it to a Brown level. C is not shadowed in this scope, so and the Brown level is 0, so it's just 0. And now we have a variable versus a Brown level, and we are trying to instantiate X with 0. Before we can do that, we have to inspect whether level 0 is available in this scope, and fortunately it is. So A is not shadowed, so we can instantiate X with 0. And now if we substitute X with 0 and reify back the names, then we have lambda A, lambda BA versus lambda C, lambda DC. Let's see another example where we have a actual name shadowing. Say if we have lambda A, lambda X versus lambda C, lambda DC. Again, we convert them, both of them, to static closures. We have AAX and the CDC. The right-hand side is the Brown level 0. And now we are trying to instantiate X with 0. Before we can do that, we have to check if 0 is available in its scope. But this time, the first A is shadowed by its successor. So 0 is not available anymore. For the left-hand side, if we apply this scope on 0, we have nothing because it's shadowed. And the right-hand side is just 0, so they do not unify. And so in this case, we can recognize, well, we have a failure. So in short, we're just changing this binary rule, and also for other rules, because we now have this scopes everywhere. So the input of unification now are 2 static closures instead of 2 simple terms. And also for the binary rule, we'll just simply extend the scope. And when we have to compare variable names, we are gonna use the name, the static closure to decide the equivalence of their names.
All right, so is that it?
Yeah, that's it.
Okay.
Pretty straightforward, huh?
All right. Well, thank you very much. Okay, so the introductions come last for this talk. So Wei Shi and Dan, both from the great Indiana University, and many people here probably knows Dan as sort of the originator of all the Kanren and miniKanren stuff. So it's all came from Dan. Well, okay, so this is very interesting to me because Dan and I did a nominal logic programming system based on nominal unification a number of years ago. And so that's an alternative to higher order unification and things like that. So, so is part of the motivation here that you could use higher order abstract syntax and use that to represent alpha equivalents and so forth instead of using nominal unification? That's part of the motivation, is that correct, for having a higher order unification algorithm?
Exactly. This is like nominal plus beta, and actually the original idea of static closure is just inspired by nominal unification. So if you think about nominal logic, it has this swapping thing.
Mm-hmm.
And so swapping is like you combine two scopes together, and this is like split swapping into two parts. And so I think this is easier for the higher order case, and also potentially more efficient. But
Okay.
it's not proved. Yeah.
Well, one issue that I've run into a number of times with AlphaKanren, which is the nominal logic version, is that there are restrictions on where you can put logic variables. So you can't put logic variables in the binder, like positions, and there are certain positions where you can't put logic variables, which makes it hard to write your programs as full relations for doing things like program synthesis. So with the approach you're showing, can you write everything as true relations, or are there restrictions on where you can put fresh logic variables?
I have a quite long answer for your question. So yeah, the idea is, if you think about these two non-first order unification branches, nominal and higher order, they both have their constraints to be, to be decidable. So like if you think about the higher order unification we are working on is actually called pattern unification. It's a subset of higher order unification. For the application form, you can not have fancy stuff if your head function is a unification variable. So and someone has already proved this nominal unification and higher order unification, they are reducible to another. So I guess the constraints that you have seen probably is related to the pattern restriction.
That's probably true because there's also extensions to nominal unification, like equivariant unification, where you're allowed to put logic variables in additional places, and that's probably like removing the pattern restriction.
Yeah, maybe. Yeah.
Okay, very interesting. If anyone has questions, feel free to type it in the Q&A. Also, I think Greg might have a question. Yes.
Hi. So I was curious about whether the broken version of the system, if it's possible for that brokenness to affect the logic itself. Is it possible to somehow make the entire logic inconsistent, or is it restricted to just unification of lambda terms and having them pretty print in the wrong way?
So by broken, if you mean like the
I mean without your enhancement to the system.
Yeah. So so first off, the we can say the unification is somehow broken because it doesn't handle name shadowing, but you can always add some preprocessors, like you can JSON our variables, make them unique, so you don't have name shadowing. And you can make your reifier smarter by recognizing the name shadowing problem and just properly rename those shadowed problem in your answers. But it will just it's at odds at this miniKanren principle that is makes things easy and straightforward. So what we want is like a plug-in solution for unification, so that we don't need to touch other parts, like having a preprocessor or change the reifier. So yeah, if we don't have this extra processors, the the current programs will be kind of broken, breaking the logic.
So you would be able to prove something like 3 is equal to 4?
Or true is false.
So like hash T is equal to hash F?
No.
Only the church encoded version
yeah,
of?
The church
okay.
Encoded.
So it's limited to the lambda sublanguage then, the brokenness? Right. Okay.
Dan, your voice is a bit low.
Any better?
Talk right on the mic, Dan. It's very hard to hear you.
Are you speaking? Because we still can't hear.
Still no, cannot hear you.
Well, while Dan is figuring that out, we still can't hear you, Dan. There's a question from Michael Ballantyne, which is, why is a solution that requires changing the reifier undesirable?
Why is undesirable? It's not undesirable if you desire to change the reifier. But what we want is a plug-in solution for just higher order. And just imagine you have a microKanren implementation. The only thing you need to do is to implement a new higher order unification algorithm, and when you call the equal operator, you just call a different function. And that's just straightforward, and maybe you can switch back and forth if you need to, because it's very hard to get a efficient version of higher order unification, but it's pretty straightforward to have a efficient version of a first order unification. So occasionally you might want to switch back and forth. So that's probably one reason that you don't want to touch the other parts of the Kanren implementation.
Thank you. Dan is still having trouble hearing you. Okay. Well, a reminder that we have the first keynote coming up in 25 minutes. That's going to be Nada and Min talking about adventures in extending miniKanren. You want to see that. And in a minute, we'll see if we can hear a word from Dan. In a minute, we will take a break and people can go to the lobby. And we have 2 different tables in the lobby for the miniKanren sessions. And if you join miniKanren table number 1, that's where people will be hanging out. Okay. Well, thank you very much, Rishi and Dan. And Dan, maybe your audio will work better in the lobby at the table. I don't know. Yes, I'm sorry we can't hear you. Somehow this feels very typical. This wouldn't really be a Dan experience if we didn't have an audiovisual problem. Okay. All right. Well, thank you, everyone. And remember to come back for the keynote, please. In 23 minutes, first keynote. And miniKanren 1 table in the lobby. Thank you very much.
Glad to see you again.
All right, so we'll take a break and we'll close the room now.
Well, that's weird. Since I'm a speaker, I can't enter as audience.
Oh, well, I'll remove you from stage.
Okay.
Unless you want to stay here.
No.
I mean, it looks like this is joint work with Michael and and Will. So I'm happy to bring them on the stage as well if you prefer, Nada. And if they prefer as well.
You mean sorry, I didn't catch what you said.
Like if you want them up on the screen, I can bring them up as well.
Yeah, sure. It's up to them. I think you can bring them if they want to. Yeah.
Okay. I think Will. Okay, I'll invite Will one more time, and then he can decide to either accept or decline.
I think Will said he prefers to lurk.
Oh, okay, so he rejected. Okay, and when Michael is here, I'll invite him as well. See what he prefers. So we'll get started in a couple more minutes, just to give people a chance to come back. So again, we'll get started in about 1 minute just to give people a chance to come back into the session. All right, so we'll get started in about a minute. Okay, so it's 9 on the dot Eastern time right now. So maybe we'll get started. So we're very excited to have Nada Amin speak at the miniKanren workshop. Her keynote today is titled "Adventures in Extending miniKanren." Nada Amin is an assistant professor of computer science at Harvard Seas. And many of you already know her. She was the co-organizer of the first miniKanren workshop and is a steering committee member. She's one of the reasons why we have a workshop today. And one of the focuses of her work is metaprogramming in the functional space. She also did a lot of work involving reflections and stage evaluation. And we're very excited for her talk. So let's... I'm going to play the video.
To Adventures in Extending miniKanren. I'm excited to present this talk here. This is joint work with Michael Valentine and William Bird. So what we'll see today is 3 things really. One is stage miniKanren, which adds multi-stage programming to miniKanren. The other is CLP SMT miniKanren, which adds SMT solving to miniKanren. And we'll look at an extension pattern that applies to both these projects in terms of how to extend miniKanren with extra things in the state object. And a few other things we'll learn along the way is turning interpreters into compilers, learning about SMT solving, and we'll see immediately now an application to synthesis. Here we have the Fibonacci function and accumulator passing style. And what this means is that we have 2 extra arguments for the accumulators A1 and A2. And once we reach 0 for n, we return A1. Once we reach 1, we return A2. And then we increment these as A1 becomes A2 and A2 becomes A1 plus A2. And we subtract 1 from n every time we loop around. So then we can call fib with the accumulators 0 and 1 to get the Fibonacci sequence. And now we can think of these examples here as test cases. And we can ask a synthesis question, which is, given the skeleton of Fibonacci, can we actually infer the step 1 and step 2? And can we infer the accumulators like 1 and like 2? So what we would like is to obtain the code at the top, given the holes here at the bottom. And there is a catch though, again, which is that we would actually have to write it this way. So instead of writing Fibonacci 0, 1, we should use piano numbers. It doesn't change the main Fibonacci function because 0, sub, and plus can deal with piano numbers instead of dealing with regular numbers. And then here we have Z for 0 and S of Z for successor of 0. So for example, 3 is S of S of S of Z. And so we can use the same problem, but this time not using built-in numbers, but using piano numbers because we don't have that feature in miniKanren. Okay, so how are we going to solve this problem? So let's look first at a Barliman solution, which looks like this. So it takes about 8 seconds of CPU time. And here we're giving the skeleton. And then we're saying A and B are unknown. These are the steps. And then we're also using fibabs on the actual examples. And we're giving unknown accumulators. And then we give the result here for this, the Fibonacci sequence. And finally, what we get as a result is the code and the accumulators. And that's because if we look at the top here, we have the definition and the accumulators. So that's what happens, and it takes 8 seconds to run. Now let's see if we can do better. So we will look at staging in a bit, but the staging solution is basically that we define a stage relation with our steps and our accumulators. And then we write this in a similar fashion where we have holes for the steps and the accumulators. And that's just the staging function. So we create a relation for that. And then we apply the relation on unknown steps and unknown accumulators and with the actual output we were looking for. And we get the actual synthesized snippets. And so this runs in the staging relation itself runs in 0.05 seconds, and the actual synthesis runs in 0.5 seconds. So that's a huge speed up, and not all problems are like that. So there are some problems where Barliman does better, but they're doing different things. So Barliman has a lot of handcrafted optimizations, while the stage interpreter is a principled sort of interpreter turned into compiler approach, and using the interpreter from the faster miniKanren repository. So we'll come back to that, of course, and then finally we can see the version of this using CLP SMT. So here we have actually added true numbers in the interpreter, and these 0 sub n functions work on numbers. And here we have the input cases and the output sequence, and here we have the skeleton result. So sorry, here we have the skeleton result, and here we have the actual result. So what we see here is this is actually quite slow. It's 32 seconds of CPU time. And the reason is that it keeps calling the solver to solve these arithmetic operations. So there's future work to do to make this faster. but it's still neat that we can write this directly using numbers. And just to give other examples of numbers we have in the system, we have here, so say 3 plus 4 is equal to 7 and things like that. So yeah, that's it for the introductory example. So what we've seen is that we have this Fibonacci function, and then we give it as a synthesis problem. So given this, the first 5 Fibonacci numbers, or 6 rather, can we synthesize the step and the accumulator? And we can in 3 different ways with different performance. But that's interesting that we can do that. Let's look at the basics of stage miniKanren. So recall in miniKanren, if you run a query with a unification, the unification happens right there. So I get a 1. And that is the possible answer for Q. Now, if I run the same query, but use a deferred unification instead, so later LL, later equal, then what I get is that Q is unbound. And then after the bang bang, I get code that says that Q unifies with 1. So just to play with this a little bit, this is a pretty simple facility. It doesn't do any simplification. So if I do list 1 equal list Q, then I get these const pairs here, even though they're not necessarily. We just want to unify 1 with Q. And similarly, if I do 1 equals 2, then that would fail as a normal query. But as a stage query, we defer the failure to the second stage. And we can use the later operator directly. So run stars Q L equals Q1 is the same as run stars Q later equals expand Q expand 1. Okay, and now we can do a more interesting thing with a staged operation. So run staged runs the query in 2 stages. First, it does it generates the data code, and then it runs the data code. So if I do Q1, I get 1 because it's running the first stage and finding something that looks like this. And then it's running the second stage, and then this returns 1. So run stage forces the code in the first stage to be deterministic. So if I did something like and that returns an error because the staging is non-deterministic. There are 2 possible results during staging time. However, I can use a later code explicitly to do that. So if I wanted to actually have a conditional in the generated code, I could do and then I get the result 1, 2. So that's the basics of stage miniKanren. We're not showing anything here that has to do with the interpreter and with Evalo. These are really the primitives that you can find in miniKanren. So this in stage miniKanren. So this L equal, this later operator, which is more general, and this run staged form, which allows you to run a query in 2 stages. If we write a relational interpreter in miniKanren, we can turn functions into relations. So for example, we might have a proof checker that we turn into a theorem prover. And if we stage the interpreter, again in miniKanren, we can then turn this proof function directly into a proof relation without the overhead of the interpreter. And in general, we can turn interpreters into compilers. So the idea is that an interpreter is something that takes code and additional input and produces a result. And staging is a process that produces code. And by staging an interpreter, which takes code and some symbolic input, we can generate second stage code that, when executed with actual input, produces a result. And so going back to our picture here, what we see is that the stage interpreter is a compiler from a functional code to relational code. So it turns functions into relation via compilation. Now let's look at some examples that involve the staged interpreter, evaluate stage. And here is an example where we have defined the map function to be in the context. And then we do map lambda x with some unknown code here on ABC, and we get the output A.A, B.B, C.C. So intuitively, we know what must go here. It should be the constant of x to x. So let's run it and see what happens. And we get indeed const xx. And if we run it in the unstaged evaluator, we would also get the same thing. So the difference here is that we use run stage, evaluate stage versus run and evaluate stage. So now let's define a stage relation, which we define it using a function and turn it into a relation. So here we have the append scheme function, and then we turn it into a relation using evaluate staged, where we give the inputs xs and ys, and we get the result zs. So let's define this, and this is how long it took to stage this function, so not very much. And now we can call it like the regular appendo function, and it behaves exactly in the same way. And in fact, if we look at the generated code, it's pretty much the code that you would write by hand, modulo these constraints that come from the interpreter, which we can't ignore for correctness, just to match the interpreter semantics. So let's take a look. So that's what it looks like. These are the constraints. Apart from these constraints, we see that we have low-level code that matches against the result to get the appendo. So here we see that if we have the empty list versus if we don't have the empty list, and so forth. So we can see that it has compiled away the interpreter loop. Let's look at a bigger example taken from the ICFP Pro 2017. Here we have a functional evaluator that understands quasi-quotes, and it's running inside the relational interpreter, here the stage relational interpreter. And so what we get is a relational interpreter for that handles quasi-quotes. In the original Perl, that had the overhead of the base relational interpreter, but here, because we're using eval stage, we're actually turning this eval quasi function into a relation without much overhead. So let's see what happens then if we run this code. So it still takes a while because it's doing this client search, and here we don't have the luxury of Bartleman's optimizations, but it's much faster than the equivalent original program. Okay, so it returned this expression, which is indeed, if we look at it, is indeed self-evaluating. So that's good. And then in general, what we can say about our staged interpreter is that run stage, evaluate stage should produce the same result as run, evaluate stage, modulo something, so modulo errors, because the stage interpreter might catch errors early, modulo the answer order, and modulo the representation of closures, because the closures in the stage interpreter contains stage code as well as no stage code, respectively. Let's now look at the stage interpreter. In the same way that the relational interpreter is a miniKanren program, the stage relational interpreter is a stage miniKanren program. And the idea is that we have the expression, which should be more or less known. And if it's known, we can generate code that is specific to that expression. However, we want to make sure that we only generate one answer. So if the expression is unknown, we want to fall back and generate code that calls the on-stage interpreter here. So for example, here we check that if expression is a variable, then we generate this call to the on-stage interpreter. So we will have explicit calls in the generated code in places where we don't know what the expression is. Now, if we know what the expression is, then we can dispatch on it as we do in the normal interpreter. So if we have a number, then we return we unify the expression and the value in the second stage. So using this later to construct an equal. And I'll come back to the stage parameter here. Well, let me just tell you right ahead, we use it so that we can do the inlining for closures. So when we have a closure and we know exactly which closure we're talking about by using stage false here, then we can just actually apply it by extending the body as we usually do. Now, the rest of the stage code is referring to the case where we have a rater and runs. And that's, now we have to consolidate the cases that are in the normal interpreter because we want to make sure that there's only one deterministic answer. So for example, here we check that the runs have a ground spine. Otherwise you have a way to go non-deterministic. Or here we check that the parameters are ground. So that's the basic of it. Just to give some idea, I'm going to show the if primo expression. So here, if primo actually is a little bit more involved because what happens is that we have those branches and we want to make sure that each branch stays within its own scope. So that's what later scope does. It ensures that that when we call this goal here, we put everything that the goal generates in C2, and then we ignore everything that was recorded, like the state object that was recorded for the later scope. And then we can generate a condi with C2 and C3. Maybe let's look at another case. Which case would be interesting? So let's see. So let's look at car, for example. So here we just unify in the second stage the resulting val that we care about and the argument to the car once evaluated. And then we make sure that val is not a special tag. So if we look at the node tag row, these are the special tags that we use in our interpreter. So we don't want them to be also used by the user directly. So just to recap, we have this eval expo, which takes whether we want to stage right now or not, and then the expression, environment, and value as usual. And then we assume that the expression is mostly known. This is what we're going to be staging for. But if it's not known, we manage to also handle this case by using later calls to ueval expo here. And just to show as well how closures are handled. So here, if we have a procedure, we have the rater that we saw earlier, and then we evaluate to a procedure. And here we put false for the staged parameter because we want to know exactly what this procedure is. And if we get a closure here, then we can start evaluating the body. And if we get other things like if we get a prim for a primitive, then we also can evaluate it as a primitive and so forth. Hopefully that gives you an idea of the stage interpreter. Let's look at some benchmarks now. First, I will describe the column. So staging is the time it takes to run the first stage, so to get the generated code. Staged is the time it takes to run the second stage, so to run the generated code. Run stage is when we lump the first stage and second stage together in the run stage form that we've seen. And unstaged is when running the completely unstaged version of the code. And of course, the gain is comparing the unstaged version to either run stage or staged. Okay, so we see substantial gains here. And sometimes the unstaged code times out after 5 minutes. And so we can calculate a minimum ballpark gain. And here for this synthesis of fib, which we've seen earlier, one of them, we see a huge difference in the staged and unstaged behavior. Okay, so let's describe the benchmarks in more details. So first, parse is for parsing with derivatives. And what the relation does is that it takes a regular expression, a token, and produces the derivative of the regular expression with respect to this token, which means what would the regular expression looks like after we consume the token. And the parse backwards means that we set the initial regular expression to be unknown, and we find it by reversing the derivative. And proofo is our theorem checker turned prover. And we see that for bigger problems, the unstaged version times out. NFF stands for negated normal forms. So here we see that the gains are good, but not substantial still compared to the others. And then here we have the piano fib examples. Let's take a look at CLP SMT from a user's point of view. So we're using logic programming or relational programming, and we're hooking it to an SMT solver. So what we have here is assertions that go to the SMT solver. So here we're saying the variable Q is greater than 0, and it's also less than 2. So mathematically, it has to be 1. And here we're saying we have 2 variables, and they sort of fall into this pattern where they're both greater than 0, and then x is equal to y plus 1. So if we run this for 3 answers, we get 3 answers here. And we can also use Condi. So the point is that miniKanren does the search, and the SMT does the constraint solving. So here we have 2 answers because we have 2 branches. And yeah. And now let's look at Factorial. So Factorial is using SMT solvers. There's a lot of asserts to the SMT solver. And here the recursion is done by miniKanren. So we're unfolding the computation. We're unfolding the request to the SMT solver. Okay, so here we get all the factorial numbers. And that takes a little bit. And then we can also do factorial backwards. And here, 6. And now we can have an evaluate interpreter, a relational interpreter that understands integer operations, so like plus. And here we have factorial written as a function, and we can do the same tricks because evaluate turns functions into relations. So here we can run it backwards. And here, this is running, sorry, this was running forward and now we're running it backwards. Okay, so we get 6. And now here we make sure that we quote the result so that we don't get miniKanren operations. Like here, if I did 2, I would get miniKanren operations. See, so quoted 6, and I could get more, but let's just leave it at that. And here we can run it with the quotes so that we can test if there are more answers than 1. Okay, and we get just 6. And here we can do a little bit of symbolic execution. So we say that the result is bar. So what should Q be here? If the result is bar, so Q should be anything but 137, and that's what we get. So it has picked, okay, so here it's picking different number as the one in the solution, but they're all not 137. And here we can ask similarly, if we get the answer foo, what should this be? And we get this number here. Okay, and now we can do a little bit of synthesis where we have this operation here and these 2 expressions. So we're giving it a template for what things should look like. It should look like this or like that. And then we're looking for F. And so F should satisfy that F1, F2, F3 is equal to 2, 4. Sorry, F1 and F2 is equal to 2, 4. So if we run this, we get true, and these were the results. So yeah. Okay, so this is what I wanted to show you. And Yeah, so one thing we'll do now is look under the hood of this. So here is the SMT log generated for the query Faco backwards 2. So just asking what is the number such that the factorial of this number is 2. And notice that we do a run star and we get only one answer. And here is the query which succeeds in giving one answer. So we see that it has unrolled the loop. So first it went on the second branch, and then finally at the end it goes to the first branch, and so forth. So let's look at the model generated for this because it's satisfiable. So we get the model where the variable 0 is 2, the variable 2 is 1, 1 is 1, and 3 is 0, and 4 is 1. And the one we care about, of course, is the variable 0 here. And what we can see is how does the run star itself work? Well, if we look at the last query that the SMT solver did, then we see that it has this extra clause here that says we want an answer that is not the previous answer, matching the model here. And we see that this is then unsatisfiable, so we know that we're done with all answers. So that's in a gist how the SMT solver works in the context of miniKanren. So miniKanren does the search, does the high level arguments, and then it unfolds everything and sends it to the solver. So let's see how we can augment the state with extra information. And we will do this in faster miniKanren, originally written by Michael Ballantyne. And it's pretty similar in canonical miniKanren. It's just that faster miniKanren is faster, so we might as well use that. And so here, the original representation of a state in faster miniKanren is a substitution and a constraint store. And what we do is we augment it with an M for extra things we want to store in there. And we change the interface from a const to a list of 3 elements. And so we have to propagate those changes, and there aren't that many of them. And that's basically what we need to start the pattern. Then we can see how to implement a log extension. So all it does is that it logs extra stuff on the successful branch. So here, for example, we have log hello, log world, and we get hello world. Or we can log into different branches and we get the logs into different branches here, different answers. And here we can have a pendo that logs B every time it takes a recursive step, and A for the base case, and we see that we get B, 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 A. So how do we implement this? Well, it's a simple thing, really. It's just this log thing takes a line, and then it's a goal. So it takes a state and returns a state. And we say it's the state that modifies M, and it modifies M such that the line is added to the state M. And this is something we had defined here. State with M, so it gives the substitution and the constraint store unchanged and modifies M. And then finally, for reification, to be able to see the result of the logging here, we actually, when we walk the final thing to reify, we actually check if M is non-null to return the M as well after a column. So that's all there is to this very simple extension, but this is basically what the pattern is about. It's about extending the miniKanren implementation to have extra information. And this is just a mechanical interface change. And then it's doing things that are specific to the extension. So here, this logging function and then this verification for the login. Now let's take a look at the implementation of stage miniKanren and see how it fits the pattern that we've just described. So here the leader construct takes something, and then it's a goal, so it takes the state, and it creates a new state. And the last thing in the new state is what we've just added as code, and then the rest of the code here. So we're just accumulating code in this in our state object for in order to do staging. Now later scope, which you've seen for handling branches, like the if branches in the staged interpreter, what it does is that it's basically calls a goal, this goal here, on a new state with a new layer of constraints that are generated, and then it generates the constraints, and then it basically ignores all the state that was used and generates and gives back the original state. And in the meantime, it sets this out variable for the code to whatever we get from walking the state of the code. So here, if we look at walk later, it basically takes some line of code here. So we get our code from the state 2 and some substitution. So we get our substitution here from the state 2 as well. So we're keeping all this information that we got executing this code, but we're keeping it local. And basically that's the gist of it. Now there is some work to generate the constraints locally. And here we can see that L equal equal is just a later of equal equal. The expand annotations here are so that we generate, if we have L equal equal const 1, 2, const 1q, then we want to generate equal equal const 1, 2, const 1q, as opposed to generating equal equal 1, 2, 1q. So the expansion makes sure that we're actually doing this, recreating the const cells verbally as a const here in the generated code. And for CLP SMT, the pattern is similar. We keep adding, accumulating the SMT commands into the state object. And when we do a Z assert, we accumulate, but we also check that the solver is still can still satisfy the answers. And it's only at the very end when we verify that we actually ask for the model of the solver. So I hope you had fun in this adventure, and hopefully it's the start of many more to come. So in terms of the code, the stage miniKanren repo is here, and the CLP-SMT miniKanren repo is here. And I've also created those branches at ventralog on both faster miniKanren and the canonical miniKanren, so that you can experiment with adding your own things to the state object. Okay, so that's it. Adventures in extending miniKanren. It was fun preparing this talk, and I hope you enjoyed listening. Thank you.
Thank you, Nada, for the talk. So if you have questions, please use the Q&A tab to ask your questions. Or if you let me know that you have a question in the chat, that's okay too. Okay, so there's a question from Alexander. I'm going to invite you to the stage to ask your question.
So for the factorial examples, so if you try to run the code backwards with something that isn't factorial, does it like realize there is a solution pretty quickly?
Yeah, that's a good question. So it depends how you write the factorial function. So if you write it by saying the base case is smaller or equal to, then it will realize that there isn't any solution. If you write it with the base case being just equal to, then it might get into an infinite a negative cycle trying to find things.
All right, thank you.
Right. Are there other questions? I have a question while we wait for the next question, and it has to do with the resource allocation in the CMT edition. So miniKanren traditionally uses interleaving search, and I'm curious how the SMT solver works with the interleaving search, if that makes sense.
Yeah, that makes a lot of sense. So we've tried a few things. So the basic thing that we're doing is basically recreating the solver state each time you make a query. So so you don't have to remember anything, but you have to every time recreate the entire state. Another thing we did is trying to use a way to turn assumptions on and off in a query, so then you can actually you can reuse part of your query that was in the same depth first search, in the same interleaving search path, but then you actually have to like pop. So instead of popping things on and off, you can actually turn assumptions on and off dynamically. So that allows you to share some more of the state between calls. So you're right. There's a problem of, I think that's where the bottleneck is in terms of dealing with this. So the problem that every time you call the solver, you have to recreate the search. You have to recreate the strategy, and in some sense, with other solvers that I've written in Scala using depth first search, then you don't have the problems. Things are much faster because you can just push and pop the state onto the solver. So that's a big question, and we've tried different things. Michael Ballantyne in particular tried a few things to consider speeding this up.
Yeah, thank you. There are other questions. Maybe I'll also invite Michael to the stage. Oh, so there's a question. How general are the staging techniques? The examples shown are for the scheme and miniKanren interpreter, but can I use the same technique for my miniKanren in miniKanren interpreter?
Yeah, that's a good question. So the idea is if you have a program that you can stage. So now we're staging the interpreter program, and we had to do quite a lot of work to be able to stage that because it was our first program that we tried to stage seriously. But I think if we can provide better primitives for staging interpreters, then we could also, or staging programs in general, then we could also handle staging miniKanren and miniKanren. I think that would be a great thing to try. So in general, the staging constructs are pretty general, and then the techniques for staging an interpreter, we've ironed out quite a few of them using the stage interpreter. And more generally, we could try staging other programs. So here we focus on one program.
But it is still a bit of a manual process to do the staging right now. It's part of the things that we're thinking about for future work of how to make it less manual, be able to take something, take your miniKanren interpreter and just add some annotations or something.
Right. I have another. And Rafi says thanks in the chat. So I have another question, and it has to do with. I guess it's more of a general question. So you've shown a way to extend miniKanren, and I think a lot of people watching, people attending the session have their own miniKanren extensions. Do you think this approach allows composability of different extensions? And how important do you think is that composability? So, for example, have you tried combining the two extensions that you've talked about today?
Yeah, so I haven't tried. I think in general, adding things to the store, I mean, you just need a convention for what you add to the store, and then you could handle many things. Now the problem is whether the extensions interact. So for staged miniKanren and CLP SMT, I think it becomes a little bit difficult to think about. Do you stage the calls to in which stage, the first stage or the second stage, do the calls to SMT happen? And that's where the problems are when the features interact. And I don't think there is a general answer to that. I think it really depends. And even for this particular case, we could try many things, I think. So one thing that would be interesting would be to do all the SMT calls in the first stage during code generation. And then we would have a second stage that is free of SMT calls, and that would be faster this way. But I'm not sure if it's possible given the use cases that we want.
Yeah, that makes sense. The interaction is the challenging part.
Yeah,
for sure. So there's another question in the chat. So I'll show that on stage. Greg, I think you have to unhide yourself.
Yeah.
Hi. So does the question make sense?
Yeah, the question makes sense.
Do you want to read out the question?
How do equality constraints work for the stage lambda values produced by the relational interpreter? Is there any higher orderness that gets in the way?
Yeah, so there is something that gets in the way. So for the stage lambda, we keep in the usual closure information, but in addition, we keep a procedure, an opaque procedure. So when you try to unify those things, you're trying to unify procedures, and that doesn't work very well. So that's an issue. I mean, I guess it's a little bit tricky because we want that information during the second stage to be able to call lambdas faster, like to be able to call them using the generated code. But I don't know if there's a way to maybe change the reifier or change the unification so that it ignores that field or does something like that. So that would be one way to solve it.
Yeah, that makes sense.
So if you have other questions, please ask in the Q&A or in the chat. So I have another question, and it has to do with the recipe that you've written. So again, that recipe for extending miniKanren. When do you think people should or should not use this strategy? So I guess like partially limitations, partially pitfalls, and sort of like are there things that people shouldn't do?
Yeah, that's a good question. So I think it's not a very like deep recipe in that it's sort of at the surface when you're accumulating things in the state object and then want to do something with the state object. So I think the use cases that are usually handled by meta interpreters, which will be the next talk, then they could be handled by this recipe natively in miniKanren. Now, I think I think when it should not be used is when, of course, if you're changing the constraint store, or if you're doing some invasive changes to miniKanren, then the recipe is not going to work. It's really just to add your own extension that is sort of that you can think of as an add-on to the state object. And but it does work when you're doing that, and then you're doing something sophisticated with the state object still. So, for example, in stage miniKanren, we're doing we have these constructs that, in addition to just adding to the state, sort of add locally to the state, or in CLP-SMT, every time we add an assertion, we can actually go and call the solver. So you can do these things as well. But the main idea of the recipe is, if you need to keep state, just keep it in the state object, and then use that whenever you need to.
Thank you. So we have another question. Greg, do you want to read it?
Sure. So the implementation of Eval Stage is quite gnarly. Do you have any design ideas for simplifying the staging interface to make its definition more straightforward, like Eval on stage?
Yes, I want Michael to answer this question, because he has lots of ideas about that.
Yeah, so right now there are sort of, I can think of two off the top of my head. It's been a month since I was thinking about this, but there are two things that you have to think hard about. One is what you had asked previously about the lambdas, the higher order part. And right now that's something that you have to do manually with sort of project and scheme level code to pass those around and identify the situation when you actually have a lambda that you can call versus a case where you have to use sort of a slow path and not. And you have to make sure that the slow path and the fast path are semantically the same. So I think it would be possible to come up with a language construct that basically stands for, you're going to call a relation, and there's two places. There's a place where you might define the code for it by staging, and there's a place where you might call it in an unstaged way. And I think there's a way to come up with a syntax that integrates those places in a way that sort of automates the task of making sure that those line up. And then the other challenge is that you have to make sure that the part that you stage is deterministic, so that you have one residual program. It'd be okay if there were finitely many residual programs, but you wouldn't want infinitely many. So you have to make it, right now you have to make it deterministic. And so some different evaluation strategy there that doesn't force you to reshuffle the structure of the relation to make that happen would help.
That makes sense.
Right. Does anyone else want to join in on the conversation? Please use either Q&A or chat, or raise your hand, whatever you want to do. So in the meantime, I have another question for you, Nada. So you were talking about these adventures that you went on, extending miniKanren. So I'm curious whether anything surprised you during these adventures. What was sort of your process, and whether anything was like harder or easier than you expected?
So I think the implementation part was easy in both cases, like the initial implementation of the constructs, thanks to the extension pattern. But what was difficult was trying to apply the extension and see if it could do anything useful. So it took us a long time to get to the point where stage miniKanren felt useful, and that's when we started using the stage interpreter and have some sense of some principles on how it should be written so that the results make sense. And so I think it took us by surprise that that it was so good at answering some of the queries, like even the double quine, the quasi quote evaluator. That was a bit of a surprise that it was so fast. And yeah, and so for some of the problems, it took us by surprise that it actually works. And I think this pushes us now to try it on more problems and on more systems. So maybe miniKanren and so forth. For the CLP SMT, so I think we immediately got some good results, and then we stumbled a little bit on making it useful because of we're not really sure exactly what is causing the slowdown really when calling to the solver so many times. But so I think we're still looking for a killer application for the SMT solver. But I think one neat thing we could do is really, if we could integrate all the features of SMT solvers in an interface that miniKanren understands, then that could be like a sweet spot for this. Yeah, so that's what I would say. Michael, do you have anything on your side that surprised you?
Certainly, I was surprised how fast staging was and how that was a consequence of sort of the way the miniKanren search works. And just like if you think about staging a non-relational interpreter, you might expect like a 10x speed up at most, probably, usually, because you're removing interpretive overhead, but kind of not so much beyond that. But in miniKanren, when you're removing that interpretive overhead, you're also removing a whole bunch of interleaving between branches of the search tree. So the cost that you're removing is actually sort of a lot more than, at least in my experience, was a lot more than I expected. So that was kind of cool.
Yeah, I wonder if this has anything to do with what we learned in the complexity analysis paper about sort of the occurs check being slow. What do you think?
So I think for the occurs check being slow, the situations that they were looking at there is sort of worst case complexity with really large values. And at least when we're staging the interpreter and doing synthesis problems, most of the values are pretty small. So I'm not sure that we're looking at scenarios that are in the same space that the complexity analysis tells you a lot about.
Okay, interesting. And regarding the use of the SMT Kanren, just from a pedagogical perspective, teaching miniKanren, the fact that you can't use numbers is such a sore point. So I'm actually pretty excited about being able to show students miniKanren without having to go through Oleg numerals and have examples that make sense. Okay, are there any other questions? So last call for questions before we go on break. All right, thank you, Nada, again for the keynote.
Thank you.
And just like before, we'll take a break now. We have more paper sessions in half an hour. And in the meantime, we'll be going to the lounge. So there should be a miniKanren 1 table. So I think that's table 17. So if you want to hang out, we'll meet you at table 17, the miniKanren 1 table in the lounge.
I love how Aramid just steals you from the lounge.
Yep.
Oh yeah, sorry about that.
No, that's okay. We can pick up the conversation later.
Yeah, sorry. So we'll get started in like a minute, and I guess we'll just hand off the floor to Michael. And let me just pause this video.
All right. Well, it's 10:30, so people are trickling in, but we can get started. So welcome to the second session of Papers in the Day. And we'll have 3 talks, half an hour each, and then another break and a keynote after that. So the first one is about meta interpreters and prologue style. So if you haven't yet had enough metaprogramming with miniKanren in Kanren or staged miniKanren, we have yet another kind of metaprogramming for you. So let's roll the talk.
Hey, Nada, what are you up to today?
I'm at the miniKanren workshop.
Oh, great. So am I.
So why don't we present our paper, Prologue Style Metaprogramming miniKanren? It's joint work with Tia Krumpf.
Sounds fantastic.
And for people who want to play, the repo is github.com/metamk.
Hey, Nada, how are you doing?
I'm fine. How are you?
I'm doing great. I just came up with this brand new type system called the Simply Type Lambda Calculus. I found it in a book. Apparently it's from the 1930s. And I'm very excited about it. And you can see the rules. I sent you the rules. They're there on the right of your screen.
Oh, thanks. Yeah. It's a pretty slick type system, only 3 rules.
That's right. Variables, application or procedure application, and abstraction or lambda. And I've got an implementation of those rules, which you can see on the left-hand side of your screen. I've been very excited to try this type system out. We can do, in miniKanren, we can do type inference. We can do all sorts of interesting things, actually. We can even do type inhabitation, where we give a type and we try to infer the term, or we can say, here's the term and what's the type. But there is a problem that I've run into. So sometimes...
Okay, let me check out your file.
Okay, all right, check out my file.
Okay, so let's see. So I can run this, run the lookupable, which is just doing this, looking up a variable in the context. Okay, let's try your examples. So this is the identity function, and we get back the identity type. So that's good. And what about self-application?
Ooh, well, it's interesting. In order to avoid paradoxes, it turns out that this type system doesn't allow for an application of a function to itself. So that x applied to x in the body of that lambda actually isn't allowed according to this type system. So let's see what happens when we run this.
Okay, we get an empty list.
Oh no, that reminds me of a famous logic programming joke. How many miniKanren programmers does it take to change a light bulb?
How many?
The empty list. So, well, that's a little unfortunate. It's not unfortunate that we get back the empty list saying that there are no answers, which is correct. There is no type for this term. But the problem is, if we're actually trying to, do type inference on a complicated program, that's not a lot of information to go by for debugging. For any program you have that doesn't type check, you're going to get back the empty list, and not anything more helpful than that. So I wonder if there could possibly be a way to augment miniKanren or use a miniKanren technique or idiom or something like that in order to change our type inferencer or put something on top of it so that we can actually get reasonable error messages or a trace of what's going on or something like that. Do you have any ideas?
Well, that reminds me of the art of Prolog. There are some chapters on interpreters and building interpreters for Prolog clauses. So I think that could work.
Okay, why don't you show me what you got?
So the art of Prolog is a great book on Prolog, but also on programming in general. And they have chapters on meta programming, on interpreters, and on unfold fold program transformations. And this was our inspiration for the current work. So now we're going to use this work to try to debug why self-application doesn't work in the simply typed lambda calculus.
Show me.
Hey, Will.
Hey, Nada. Long time no see.
Indeed, indeed. So I've got a solution using Prolog style meta interpreters.
Great. Let's see it.
Okay, so the idea now is to generate proof trees, such as this one. And here we see in red where some error occurred. And so we see that to type the self-application, we first type an abstraction. So we put X in the context, and already it has unified further. So it knows that X has to be a function because of this self-application. And then that's indeed what's happening here. And so it looks it up in the context and it sees it a function, but then it also looks this X up in the context and it sees that it has to be T1. So it has to unify T1 arrow T2 with T1, and because of the occurs check, it fails to do so.
Great. And so we can tell exactly where we failed.
Yeah, and the nice thing is that the explanation you give, the historical explanation for why self-application doesn't work, basically reduces to the occurs check to avoid the paradoxes.
Well, that sounds very useful indeed.
Yeah, so let's look at what the code for this proof tree derivation looks like. So it looks like this, and it matches the proof tree. So we just had a simple way of transforming this to the proof tree shown in the paper, and we can see that here it says that this lookup will fail because it's trying to find the type T0, but instead it finds the type T1 to T1, T0 to T1.
So basically there are two calls to lookupo, which will look up a variable in the typing context, and they have to return two different values that are incompatible because of the occurs check.
Yes.
Very clear.
Hey, Will.
Hey, Nada. Good to see you again.
Good to see you too.
Do you have any more examples of metaprogramming using meta interpreters in miniKanren?
Yes. So let's look at this graph here. In miniKanren, we can represent it as this edge-arrow relation, which says that there's an edge between A and B, an edge between B and C, and an edge between C and A.
Well, this graph has a cycle in it. So if we started asking about paths between two nodes, between, say, let's say A and C, there are actually infinitely many paths because you can keep going around that triangle as many times as you want.
Indeed. So let's look at the path relation. So here we have defined one. And the base case is if we have an edge between X and Y, then there is a path between X and Y. Otherwise, the recursive case is that we go through some intermediary Z, and we have an edge between X and Z and a path between Z and Y.
Makes sense?
Okay, so let's look at some examples. So here I have to load this example path that I just showed you, and then I can ask for the 10 paths between A and something. And I get BC, ABC, ABC, AB. And so what do you think, Will?
I think we see some duplication there.
Yes, and furthermore, we don't want to do a run star because that's what diverges. There are infinitely many answers.
Okay, so maybe we can somehow remember parts of the paths we've seen before, sort of like a memoization, so that we don't keep redoing the work over and over again.
Yes, and that's what we're going to do with the circular meta interpreter that records a trace and then sees if we've encountered a goal before. So let's see what happens when we run this. And we get indeed this answer here. So we have a path between A and B because there is an edge between A and B, so you can take this path as an axiom. And then we have a path between A and C because we can reduce this problem to finding a path between B and C. And then we have a path between A and A because we can reduce this problem as having a path between B and A, and then a path between C and A.
Great. And we are able to use a run star and prove that there are no more distinct paths.
Indeed. And we could even do this for any path between anything to anything. And the run star still works, and we get a bigger list.
So Nada, this seems like a very powerful and useful technique. Does this mean that we have to change the implementation of miniKanren to get this meta interpreter stuff working?
Not at all. It's all user level. The idea is that we write an interpreter for a user-defined relation that we reify. So we have this relation expressed as terms as opposed to expressed directly as predicates in Prolog terminology.
So when we're seeing patho in the output of one of these run stars, that means that we have to write a reification relation as an end user relation to see the pathos. Is that right?
Yeah, that's right. And we provide a macro for this, which is part of our define rel. So if we look at the XPath relation, here we see that we're using define rel. And it takes here this patho clause, which means it will create this patho clause relation, which is a reification of patho. So yeah, we could define this patho clause by hand.
Okay, let's see it.
Okay, so let's do it. So the first thing is and let me call it my patho clause just to distinguish it. So I take a head and a tail, and the head is the goal that we want to prove, and the tail is the remaining goals that are needed to prove that head. So for example, then once I have it, I could run it this way. So that's what we'll be able to do, for example. And so how do we write this patho clause relation? Well, as in here, there are two cases, and we want to explicitly match on the goal that we care about. So we can say fxy head equals, and then we have the two clauses. So if we have an edge between xy, then we're done, because we're only reifying the patho relation and not the edgeo relation. And if we have an intermediary z where we have an edge between x and z, and then we have what's left is to put in the tail a patho between z and x. Okay, so hopefully that works. So let's try it.
Is that relation not recursive?
Yeah, it's not recursive because all we've done is reified we're just reifying one step of how to prove patho clause. So in some sense, this relation is not recursive if here patho becomes a term.
Okay.
But the recursion happens here where we have patho in the tail, and then it's the role of the interpreter to turn this into a recursion.
Great. So can we see it running?
Yeah. So here we have the output. So what do you think of this output?
So if I understand correctly, when we say to prove patho AB, we prove the empty list. What that means is that patho AB is already an axiom because we have a direct edge between AB. But if we want to prove something more complicated, such as in the second line, which you have your cursor on, if we want to prove there's a path between A and some node underscore 0, then we first have to prove that there's a path between B and A. And if we can do that, then we've proved that there's a path between A and underscore 0.
Yeah. Wait, is
that right? That doesn't look right to me.
Let's look at the definition again. Wait, so if there's an edge between X and Z, then there should be a path between Z and X. That doesn't look right. It should be Y. Let's try again.
Okay. So if we want to prove that there's a path between A and some node underscore 0, we have to prove there's a path between B and underscore 0. That sounds more plausible.
Okay. And going back to your point about recursion, we're not also saying that if you want to prove a path from A underscore 0, you can do a path from C underscore 0. This is handled by the interpreter itself, what it wants to do with the recursion. This is only showing the first level unfolding of the relation.
Would it be accurate to say that the reason we don't get an infinite loop when we do a run star is that our reifier isn't recursive?
I think that's fair. If it were recursive, we would get an infinite loop there.
So somehow we have to break the recursion to get a finite number of answers.
Yeah, but there is a natural way to break it, which is following the logic of the original relation, and sort of, I guess it's a little bit like trampolining, right?
Mm-hmm. Okay, very good. So I guess one lesson we learned is that a prologue style meta interpreter in miniKanren doesn't protect you from making a mistake, but it is useful.
Well, and the thing is, this is an advertisement for our defined rel macro, because we wouldn't have done such a mistake there.
I see. So that this keeps us safer. We can't make this class of mistake with the reification.
Yeah,
so this handles the reification for us automatically.
Yes, exactly.
Okay, great. Define rel is obviously a macro. Is this some sort of complicated syntax case macro?
No, it's a syntax rules macro. Let me show you. So here we have the ID like patho, and then here we have the reified IDs. For example, patho closes 1, and we might have multiple reified IDs because they might reify different relations. And then here we also have variables that are available at the meta level, at the interpreter level. And then we have the body of the relation. And then all this macro does is to define these CIDs, these reified relations. So for example, it defines patho close. And the main way it does this is by matching here with the head of the close with the ID, and then closing off to the tail when it's done.
You mentioned an interpreter. So I guess in addition to having the def-rel macro, which is predefined for us, we're also going to have to define an interpreter to interpret the relations we care about running or tracing or whatever.
Yes, so we haven't seen yet a definition of an interpreter, but we've used at least two. So one was for the type debugger. We have a meta interpreter that deals with proofs and how to debug proofs. And we will show this very briefly. And then we had the cycler meta interpreter that deals with detecting cycles, and we use this on the cyclic graph. But let's first look at the vanilla interpreter, which is at the template for all interpreters. So it's as short as this. And what we're saying is that we have a solver for goals, and it takes a particular clause like pato clause. And then it says if the goals are empty, then we're done. Otherwise, we look at the first goal, and we look at the body or the tail of the first goal, and we solve the body, and then we solve the other goal. So this is a depth first search style interpreter, and it matches the Prolog tradition, and we can run it on the original program, the non-reified program, and get the same behavior as the reified program. Does it make sense, Will?
I think so.
Okay, so let's just look at the proof debugger, because it's quite interesting, I think. And it's not following the rules that Will likes in terms of writing miniKanren program, because there's a Condé here.
No, it's not relational.
So that's the main thing I wanted to show. We basically try to solve the program, and if we fail exactly at this body, then we say, okay, we found an error, and we instead of completely failing, we return that error right there. And so that's the gist of it. I'm not going to go into details.
Okay, I see there's another Condé and proof debug down below.
Yeah, that's a meta level thing to say, did it actually succeed or did it actually fail?
I see.
Good question. Hey, well, so we're done.
Wow, that only took 20 minutes.
All right. Well, thanks, Will. Thanks, Nada. I think you win the award for most laughing and crying emojis in your talk.
There was plenty of laughing and crying when we recorded that, believe me.
So a reminder for anybody who's arriving late, you can ask questions in the Q&A tab. And by default, if you ask a question, we'll invite you on video to ask it. And otherwise, if you would like me to read it, you can say silent in your question and I'll read it. So feel free to add those. In the meantime, I have a question I can start with. So it seems this looks a little bit different, I guess, than what I've seen before in Prolog meta interpreters. So I was wondering what motivates the different strategy. You know, in Prolog, there's a reflective clause relation that you can use to access information. And here, it looks like you're having to do something with a macro. So I was wondering why that is.
Well, so the macro tries to emulate a little bit what happens in Prolog. The reason we can't do it like in Prolog is because we take miniKanren as it is, and when you define a relation in miniKanren, you're just using a scheme relation, and so there's no recording of the fact that it is this particular relation. So it would have been, I mean, so we need a way to sort of, when we write the relations, be able to record what they are. And I guess we could have done it, we could have done it in a different way as well. So in Scala, we did it using a more stage-like approach, where we generate the reified program as a side effect of running the program. But in miniKanren, it felt more natural to have a macro. And also at the very beginning, I was actually doing things manually most of the time. And when Will saw that, he was horrified, and we wrote this macro as a result.
Oh, well, thank you, Will, for the language feature.
Yes, it's a hard-driven development.
All right. So I still don't see any other questions in the Q&A. So as a follow-up, do you think there might be any way to use the first-order representation that from miniKanren 2019 paper, I think, to sort of make the reflection work more easily? I don't know if that makes any sense.
Can you remind me of what the first order representation is?
Yeah, so in instead of sort of dealing directly with having a goal constructor like disjunction directly construct something that returns a stream, instead it constructs a first order representation of the sort of the fact that there is a disjunction here. And then there's a second sort of layer that interprets those first order representations. So it seems like you might be able to use the first order representation before it gets interpreted as something that a program could reflect on.
I see. So one thing I'm not so sure of is that in our case, we're still using, for disjunction, we're still using the inherent pattern, the inherent way of doing disjunction in miniKanren. So we're only reifying things one clause at a time, and then the disjunction is still just a condi. So I'm not sure if it would help to have a reified disjunction in that case.
I see. So what was your rationale for not reifying the disjunction?
So I think it fits with the Prolog tradition. So how you would do it by hand, if you are not to use the clause construct in the automatic reifier in Prolog, you can also do it by hand. And in that case, you would also just rely on the Prolog disjunction. You would write separate clauses for the reified version.
Okay, cool. So do you have any other applications in mind beyond those you've explored so far?
Well, I mean, so one that we didn't mention that is in the paper is doing partial reduction using that technique. So this is also based on the Art of Prolog, the chapter on program transformations. And it's pretty neat. We haven't pushed it so far. We've just reproduced the example from the Art of Prolog, which is doing a finite state machine and specializing it to a particular automaton. And I think there could be something there to explore. In general, I take it as like meta interpreters are good for rapid prototyping in some ways. And then if you actually want to do something, maybe you're better off doing an actual extension.
Or perhaps collapsing towers of meta interpreters to make it go fast?
Okay, thanks for the hint. Yeah, maybe.
All right. So if nobody else has a question, I think it's time for the next talk. Thank you both. Oh, we have one question from Andrew Keep. You hinted that the Scala implementation can use staging. Could staged miniKanren do this?
That's a really good question. So I think in Scala the reason why it's nice is because we can overload the operations to stage without changing the program. If we did it in staged miniKanren, we would have to still do the lifting explicitly in the program. So we would have explicitly to say that this is a lifted case, and this is, I mean, this is a later case, and this is not a later case. So it wouldn't look as clean, but maybe there's a way to use stage miniKanren so that instead of the manual verification, you have something that is nicer and also maybe more flexible, because the macro is actually a little bit inflexible in terms of having to verify the whole program as it is. But with staging, we can verify parts of the program. So I think that's a great idea. If I was thinking about it loud here, but I think it makes sense.
All right. Well, thank you. Next up, I think we have Evan Donahue. Let me make sure there's nothing else in the chat here.
Thank you.
And if I recall, I think Evan going to speak live? So we probably want to invite him up on stage. Cool. So it's going to be a live talk. So the next talk's on a new language construct, guarded fresh goals. It's exciting to me because it's another approach to the question of how can we integrate information from different parts of a program to more efficiently solve. We've had a couple of miniKanren workshop papers on similar problems. So I'm excited to see this one. So take it away, Ed.
Thank you. Let me just make sure I've got my screen shared here.
Be a button on the bottom next to where all the reactions are. There's a up arrow button. Yeah, there we go. Yep. So we can see your screen now.
There's an up arrow button and additionally a menu that wasn't 100% obvious, but it seems that we managed nevertheless. So here we are.
Perfect.
Thank you. Let's just still see that full screen. All right. So thank you. Yeah, good. And thank you for coming to my talk. So my name is Evan Donahue, and I'm currently a researcher at the University of Tokyo, and I'm going to talk today about guarded fresh goals, which are a form that I added to a Smalltalk implementation of miniKanren to capture the dependency structure of relations and use that information to optimize the search. So I'd like to start by defining what guarded fresh goals are and what motivated their addition. And then I'd like to sketch the intuition underlying the implementation and use that to speculate about some of the performance results that arose in the evaluation. And finally, I'd like to sketch out why this work was undertaken and what kinds of applications I'm hoping it will enable in the future. So to start with, what do I mean by guarded fresh goals? So let's first consider a common pattern in miniKanren programming for destructuring a list term. Some cons pair q is passed into some relation. We create two new variables a and d for the car and cutter of q, and we unify their pair with q. We then go on to write additional goals that use a and d.
Sorry, Evan, are you sharing a shell?
I'm sharing a PowerPoint.
Oh, okay. So we're only seeing the PowerPoint.
Yes.
And we're only seeing the first slide.
That's not as good. All right, let me
there,
see
yes,
here.
Now we see the second slide.
Okay, I think what's happening is that it doesn't want to see the entire slideshow while it's in slideshow mode. Let me try putting it in slide share mode and seeing if I can do this. Can you see this?
I see outline, definition.
Okay, I think we're good then. Yeah, so share screen wants you to tell it which application, and I think I picked PowerPoint, which is separate from its full screen manifestation. So you missed my blinking animations, I guess.
Looks good now.
Thank you. Where were we? So yeah, so a basic miniKanren pattern for destructuring a list term on the left that you've doubtless seen a million times if you've programmed a miniKanren. And on the right, the equivalent version in guarded fresh notation. So syntactically guarded fresh is just a simplified way to express this basic idea of destructuring complex lists terms to access their contents, and it consists of two parts. The first is a set of binding forms right there that pair variables with patterns, and this is similar to pattern matching forms in other languages, and perhaps, as I've recently been told, a throwback to the original non-miniKanren, although I haven't yet had a chance to explore that in detail. In this case, the form expresses that Q is to be unified with a pattern consisting of the pair A and D, where capitalized symbols in the pattern are to be replaced with fresh logic variables. After the binding forms, we just have the body expressions here that use the new logic variables A and D, similarly to the way that fresh normally works. Of course, this is not a talk about syntactic affordances. What is important about this form is that it supplies the implementation with two pieces of information. First, that the body of this guarded fresh goal depends on Q, and second, that Q is a complex term that may contain unbound logic variables. The key here is that before we evaluate the body, we'd like to know as much as possible about the constraints on Q and by extension on A and D. If we don't have to introduce new logic variables, we shouldn't. And if we do, we should introduce them once we have as much constraint information as possible to narrow down their possible values, hence the dependency-directed introduction of logic variables. Now, I should note that in terms of capturing these dependencies, the guarded fresh form itself is probably immaterial. In an appropriate language and context, I would expect this to be possible with some sort of static analysis, as I know similar things are done in other recent work. What the guarded fresh form itself accomplishes, if anything, is probably more like a bit of social engineering. By giving the programmer a simpler form dedicated to expressing a common idiom, it encourages the programmer to annotate the program implicitly with the required dependency information. In the embedded context in Smalltalk, syntactic analysis would probably be possible, but would also probably require a much greater separation between the host language and the embedded miniKanren operators due to the liveness of the image and the late binding of the method calls. A new form, by contrast, was no more difficult to implement than any other operator in the language. Now, the reason we want to track this dependency information is that it can let us optimize the search behavior in ways that are difficult to achieve through more general strategies or through manual optimization. Now, the inspiration for this work comes largely from work on guarded horn clauses for parallelism in Prolog, which is where the name comes from. Although guarded horn clauses were primarily a construct motivated by parallel processing, it was also observed that the types of search rearrangement they permitted had other uses. And this is a simplified example from a 1985 paper by Ueda. The Prolog rule consume destructures a buffer shared between two parallel processes and checks whether the next element is an end of stream or EOS symbol. If the next symbol is EOS, we're done. If the next symbol is not EOS, we recursively consume the tail of the buffer, and I've removed the code here that processes the head elements. This is purely just consuming elements from the buffer and throwing them away. In between the head clause on the left and the body clause to the right of the vertical bar in bold, we see the guard. Now, the purpose of the guard is to determine whether the rule should execute or whether it should be suspended to execute at some point in the future. If H is bound, then the disk quality can either succeed or fail. If it is free, however, the rule will suspend and await the binding of that variable. The effect is to sequence the logic of the buffer so that the results can only be consumed after they're produced. Independent of its implications for parallelism, consider the comparable miniKanren code. The relation accepts a buffer variable. It destructures the head and the tail. And it then makes a choice. If the head is bound to EOS, do nothing, and otherwise consume more of the buffer. Now, suppose in the code in which this is used, the consume relation is called before the relation that produces the elements of the buffer. Running fully relationally, the consume relation is going to produce a one-length buffer with an EOS, a two-length buffer with an EOS at the end, and so on. And each of these buffers is going to get sent to the producer, which will fail unless it tries to produce exactly that many elements. If producing those elements is expensive, then this ordering will make it many times more expensive. The main thing that guarded fresh does, if we were to write the same program using guarded fresh, is that it lets us look at the line on which the bindings are declared and determine that the body depends on the variable buffer, which is currently free. So we should suspend and wait, as we do in the Prolog code. In order to preserve the completeness of the search, if buffer is never found, we eventually do have to give up and commit to its contents being free variables and continue with the body anyway. In the case of this simple buffer, though, it's easy enough for the programmer to order the relations appropriately to match their expected use. However, in many practical cases, the order is dynamic and cannot be optimized by the programmer ahead of time. One such case in the motivating example in this talk is program synthesis. Guarded Fresh is not exclusively for program synthesis work, but the synthesis does exhibit, in a certain sense, the form of the same producer-consumer architecture. I know many will already be familiar with program synthesis, including from other talks today, but for those who are not, a simple approach to synthesizing, for instance, scheme programs in miniKanren is to write an evalo relation that mirrors scheme's eval function. If an expression is supplied as the first argument, the relation will evaluate it. If, however, the first argument is free and the inputs are supplied somewhere in the environment, along with desired outputs in the value argument, the relation will synthesize a program that accepts the input arguments and produces the desired values. Even without a bit of extra work or any extra work, miniKanren is going to be a bit smarter than just generating random scheme programs and testing them. Because we have these ground inputs and outputs threaded through the interpreter, we're going to be able to say, for instance, that if the output of the program as a whole, or even any sub-expression, needs to be, for instance, a Boolean, we're not going to be able to synthesize that with cons, no matter how many or what kinds of arguments we supply, so we can just trim that whole branch. This dynamic is important because that's what we want to take even further with the information we get from the guard clauses. Many interesting programs are going to require more than a single input-output pair to fully specify their behavior. To specify those programs, we can just conjoin multiple calls to evalo, and this is where the producer-consumer architecture becomes more apparent. Each evalo is essentially producing partial programs and sending them to the other evalos through this shared expression variable. With standard left-to-right conjunction, the first relation is going to produce a partial program and send it to the second to the third, and so on. However, different input-output pairs may constrain the behavior of different parts of the synthesized program. So, for instance, if the first 9 examples produce a list term and the 10th example produces a Boolean, then the synthesis has just spent all this time synthesizing a cons expression it will ultimately have to throw out and replace with perhaps an if expression that resynthesizes that cons and then adds another branch for the Boolean, for example. It would be better if before synthesizing each sub-expression, each of these evalos could wait and see if some other evalo could bring its input-output information to bear on constraining the sub-expression before proceeding. And that's what Guarded Fresh principally allows by letting the first evalo suspend and see if the second can contribute to synthesizing some given sub-expression. So what is Guarded Fresh actually doing? So let me preface this by saying that there's a large space of possible heuristics you could imagine, both automatic and under programmer control, that this dependency information captured by the Guarded Fresh could enable. And I'm only really starting to explore that space. So what I'll describe here is a collection of heuristics that I've so far found to be the most helpful in program synthesis, and that are what I tested in the evaluation section, but I'm not suggesting that they are necessarily universal or optimal in all cases. So that said, consider the conso relation, which is a subrelation of evalo that synthesizes cons expressions. It accepts an expression, an environment, and an output value. The expression is unified with cons, while the output is unified with the cons pair that it generates, and then the car and footer are evaluated. The broad intuition is that we are going to want to see if expr and out are free, much like checking for the EOS symbol in the buffer example. And if they're not, then we can evaluate the body immediately. If they are free, we'll want to suspend the body until we have more information about them or until we run out of other goals to try first, in which case we'll just commit to their contents being new, free, unconstrained logic variables and proceed from there. The first thing that happens is that expr and out are going to be unified immediately with their respective patterns in the main substitution. Before going on, I want to mention 2 optimizations that happen at this point. One involves the recognition that if expr and out are already bound, then there's no need to instantiate 4 new fresh logic variables and extend the substitution 4 times. So suppose expr is ground to cons of 1 and 2, and out is the pair 1, 2. Then we're just testing whether, when we're supplying these ground values just to test whether our interpreter produces the right values, just to check that this call succeeds. So with normal fresh, we would end up with 4 fresh logic variables bound to 1 and 2 potentially in the substitution, and then we would run our body goals using those variables. We'd sort of indirectly be referencing the values in our expressions. Since Guarded Fresh knows in advance what unifications are going to be made, we can just look up expr and out and reuse their subterms in the body of the Guarded Fresh. So the substitution remains the same, it's just whatever was in there previously, and we use the bound terms that we looked up in that substitution directly in the body clauses. One other heuristic optimization at this point is that normally fresh would cause a delay that passed control of 2 other branches of the search tree before evaluating its body. And as currently implemented, a guarded fresh checks whether all variables, in this case just both expr and out, are already ground or bound. And if so, we evaluate the body immediately. The intuition here is that we might as well spend our computation cycles consuming ground information rather than speculatively unifying free variables that may later cause failures. One subtlety here is that we actually want to distinguish between bound terms that genuinely constrain the search, such as those from the input and output examples to the top-level synthesis relation, and bindings that are implicit in the source code and will be made in every non-failing execution, such as speculatively unifying an expression with the cons symbol. And currently, we check this by testing whether any guarded fresh goals are currently suspended on a variable, which tells us that that variable was free when it was initially found, and that that guarded fresh goal probably did the unification preemptively and then suspended itself. It is possible to write perverse programs that infinitely loop with this heuristic, such as by trying to destructure the same ground term over and over again, but it's not clear whether this poses a problem in practice, and it has yet to come up so far in my experience writing these relational interpreters. Anyway, continuing on, although we've just unified expr and out, if either was previously free, we're going to suspend this goal. And we do this by pushing it into a data structure that I refer to in the paper as the schedule that sits in the package alongside the substitution and constraint store, and proceed with the next goal. If we push the conso from the previous slide into the schedule, it will look something like this. It's a 3-tuple with a list of the external variables that it's still waiting on, expr and out, a list of the internal variables contained inside the patterns unified with those external variables, and a closure that evaluates to the ultimate body goals. As the external variables we are waiting on become bound, we can eliminate them from our dependencies. So if out was already ground because it was part of the input and output data, for example, we can eliminate that. And if we get down to 0 dependencies, then we are back to the previous optimization where we just pull this out of the schedule and execute it immediately. When that happens, we essentially just feed the internal variables to the closure and evaluate the resulting goal that it returns. However, many variables will never be bound. And if we don't execute any of the suspended conso relations, expr will never be bound to cons. In that case, we end up with a schedule that looks potentially something like this. 3 guarded freshes, all suspended on the same expression variable, representing 3 calls to eval-o with 3 different input-output pairs, all waiting on that one variable. There may also be some other guarded freshes on other variables mixed in here, like apply and lookup, for instance, synthesized in some other part of the program. If we run out of other goals and we're down just to the schedule, we can select one arbitrarily from the schedule to continue from. And for simplicity's sake, let's pick the top one. So we remove that the top goal from the schedule, and we essentially commit to all of the external variables on which it depends. Or in other words, what we're saying is we're done waiting. Whatever we know about expr1 is what we know to the best of our knowledge. So let's treat it as bound. We're just going to remove the first tuple and actually evaluate it. And then we're going to remove expr1 from any other guarded fresh currently waiting on it. We're just deciding that we're not going to see any new information about that. That's going to bring the other conso guards down to 0, and they will be scheduled for execution next ahead of things that normally would have priority in the schedule, like the apply and the lookup. And that's essentially what causes the interleaving property, where it tests all of the input pairs into synthesizing conso. If it needs to pick a different synthesis target, it will end up being rearranged so that it brings all of its input-output pairs on that down to bear on that, synthesizing that variable as well. So that is in essence how guarded fresh currently works. You push goals that depend on free variables onto the schedule. You prioritize them if those variables become bound. If they remain free, you eventually decide to just commit to them and treat them as though they are bound and prioritize them, everything still waiting on them at a certain point. It is possible to imagine other heuristics that, for instance, prioritize goals with fewer dependencies or dependencies with more goals depending on them, or letting the programmer specify some combination of strategies. One particular dimension that may be useful to give the programmer control over is that of the default order for removing items from the schedule. So we pick the first element here, treating the schedule as a queue. And this is what miniKanren currently does, but it also comes with very pronounced implications for the shape of the overall search. Using a queue by default will make the conjunctions basically fair in the sense that every conjunct will eventually be visited and miniKanren won't diverge unnecessarily, as it sometimes does with conventional left-to-right conjunction. And there's been other recent work on properties of this type of search strategy that explore it in more detail than I do in the paper, but I think that they're analogous, very closely analogous. Conversely, if we use a stack, we would get something that more closely resembles the left-to-right conjunction in that it can diverge, but it also better respects the programmer's goal ordering, which can sometimes be useful. But in any case, let's look at how these goals hold up in practice. So I tested this implementation against another interpreter built with more traditional fresh goals on a few instances of 3 different classes of function. To get this table, I found the smallest hint required for the slower of the 2 interpreters to synthesize the full function. Then I benchmarked both interpreters starting from that hint. So the very short times in the guarded interpreter column speak in part to how big a hint the standard interpreter required. It's not necessarily a time of the full synthesis task. The first test was Boolean functions because they required more examples to fully specify than some other functions, which would test whether guarded fresh could make better use of those later examples early in the process. And as you can see, while AND was simple enough that both interpreters synthesized it fairly quickly, the slightly more complicated XOR was much easier for the guarded interpreter, which also just sort of subjectively observed was less sensitive to the order in which the examples were presented, it seemed to me, as one would predict for the interleaving, although I didn't measure that very precisely, so that could potentially go away if I examined it more closely. And next were recursive functions of lists, because synthesizing a recursive step exhibits interesting kinds of data flow. The constraints on the arguments for the recursive call, for instance, come from the partially synthesized function body by way of the environment lookup, which would be a very convoluted path to trace by hand, although I believe that some version of that has been done. As I discussed in the paper, I think there's more room to improve on this by making better use of that data flow with additional heuristics. But in any case, the guarded fresh was markedly faster precisely at handling that recursive step, which standard fresh could never manage to synthesize on its own. The one surprise was that quines were actually significantly slower in the guarded interpreter. I don't have a great theory as to why. It's true that quines, unlike other programs, only require 1 call to eval, and the guarded clauses primarily help in cases where I think that's the...
By the way, I think we lost your slide. I don't know if it matters.
What's that?
We can no longer see your screen.
Interesting. Maybe Aramid is beeping at me for some reason. Well, let's see here. I think my only other slide is future work, which has nothing on it. So I think we're okay. Let me just finish this real quick then. The one surprise was that I was testing on quines, where the guards actually not only did nothing but significantly hurt performance. So I don't really know why that is, but I suspect it has to do with the fact that the program expression and the output both being the same variable may be confusing somehow the way that you end up with sort of both inputs and outputs depending on the same variables, and that may be confusing the order in some way, but I can't really be more precise than that at this point. I also tried an interpreter with fair conjunctions with no dependency information, but that performed uniformly worse. And then to close, I just wanted to make a remark about the kinds of problems I thought this might apply to. It wasn't synthesis per se, although that is one example where there are these multiple evalos that can exhibit this sort of producer-consumer structure, what I'm calling that, where multiple relations are depending on the same variable and communicating through that variable. I know there's been other work on, for instance, linking together parsers and interpreters that share the same variable that's suggested that they might benefit from being able to more, interleave in a more detailed fashion those two relations than was easy to write by hand. And so you could potentially imagine something like that happening with with this kind of approach. And also the application area I'm interested in currently working on is semantic parsing, which links together natural language grammar parsing and a semantic representation or a planner. And so those are all kinds of relations where you have multiple different relations that share a variable and that might be able to benefit from going back and forth to share information in an order that's difficult to achieve by hand. So that's really the objective of this. I think that's everything I have. There is a link to the GitHub that you can't see, but if you search for small Kanren, you'll find it. And I think I'm a bit over time due to some technical difficulties from presenting live, but it did give me a few days to get the presentation a bit more polished, so hopefully that's an adequate compensation. That's all I have. Thank you, and any questions?
All right, thanks, Evan. Let's see, looks like we have a question in the chat. And also I can hear my audio feeding back through your computer.
Yep, I took my headphones out to present, but I'll put those back in to get rid of the feedback. All good.
Cool. So while we wait to see if there are any questions, so the thing that strikes me about this is that the other approaches that I've seen to trying to combine information from different conjuncts sort of work with like a normal form of a conjunction of disjunctions, which is something that I don't think you do here. Is that right?
Not unless it's implicit in some way I don't notice, but no, it's not.
Okay. So what would happen, for example, if you have a schedule where you've got a guarded fresh that is paused waiting for information, and you've got a disjunction, which sort of gets to go first?
So let me think here what you're trying to describe. So the disjunction, I guess. Okay, so I mean basically, insofar, so we have we've already had a. So what happened first was the guarded clause went to put something in the schedule, and then we arrive at a disjunction. Yeah. And then, so basically, in the schedule is held alongside the substitution and the constraint store in the package, and so the kind of the normal thing happens where the same substitution is going to end up in each branch of the disjunction, and they're both going to end up with essentially copies of the guarded clause that will run, twice, I guess. So potentially you could maybe that would end up being less efficient. Kind of depends on the structure of the program, but it's just going to run twice, I believe, when each branch evaluates. Okay.
Yeah, that's interesting to me because everything else that I've seen is trying to avoid splitting on branches before other things happen. But this seems to work really well too. So that's kind of interesting.
Yeah. No, I feel like, it is a bit of a collection of heuristics of just kind of getting the implementation decisions all to align in order to get the performance. And I feel like there's more I have to understand about exactly where the performance is coming from. But it feels like there's kind of, a neat idea under here that I just haven't isolated, but maybe it's just sort of, a collection of random things that are situationally specific. But it's robust enough across different program types that I feel like it's doing something important. I just don't fully have a good way to isolate it yet.
Yeah. I wonder if there would be a way to integrate it a little bit more with handling of disjunction so that you can sort of get the same benefit that you have now, but also maybe avoid unnecessary splitting of branches or something.
Mm-hmm. Yeah, no, definitely.
All right. If anyone else has questions, put them in the QA. My other question was, when you're writing a program and you're using guarded fresh, are you using this every time you analyze any variable, or do you use it specifically for analyzing variables that you expect are sort of shared in the program synthesis query or something like that?
So in the way I use it, and I suspect that there's a potentially broader range of fresh variants that could productively collaborate. But the way that I wrote the interpreter and the way I kind of use it as I'm working with it in my current style, not knowing any better, perhaps, is that anytime I am, creating a complex term, creating a list term of any kind, I'm using guarded fresh to do it. And in fact, as implemented in the Smalltalk, guarded fresh has what is essentially a convenience, although it probably has performance implications as well, which is that in addition to the pattern bindings, you can just have it create a couple of extra normal unbound logic variables just like fresh, because sometimes you need those not to be patterns, but just to pass to two different relations to constrain them to have the same argument in some position. And so I essentially use guarded fresh almost entirely to the exclusion of any other kind of fresh in the relational interpreter and in most of the other programs. And so it's like, I just kind of let it do its thing. It's possible that there's like a better way to do it, but it's not something that I'm trying to be very specific about with when I use it. And that's how this is built, and that's where the performance numbers you're seeing are coming. I don't think there are any real other forms of fresh in the guarded interpreter, with one weird exception that I found that I got a lot of performance by just kind of wrapping some of the more expensive if and apply relations in a couple of just dummy freshes to bounce them a couple of times to prevent them from expanding too quickly, which I think is partly a consequence of how I do some of the expansion in small Kanren more generally. I don't know if that's important. It was kind of a weird thing, but aside from that, it's all guarded fresh.
So one thing we got in a chat, I think, was a comment from Lisa. Not a question, but this was a serious problem with the synthesis work that we talked about earlier in the lounge, where we needed an implementation of miniKanren that supported this kind of sharing of information across eval calls.
Where is this?
It's just in the chats, I think.
Oh, okay. I see. Well, I'd be interested in perhaps the next lounge to hear more about that. I think I missed it because I think I had to step away for a second.
Okay, cool. All right, well, thank you, Evan. Next talk. And I think next up, we have a talk from Endogene about universal quantification and implication. And I think our hosts, Greg and Lisa, are also involved in that one.
Oh, wait, I just wait for it to start, or? I am Endogene. This talk is about universal quantification and implication in miniKanren. This is a joint work with Gregory Rosenblatt, Matthew Might, and Lisa Zhang. This work is adding two new Go constructors, universal quantifier and implication, into miniKanren in a way that works well with our existing primitive constraints and the recursive relation. These are the two new Go constructors that we introduce. For the universal quantifiers, the full Go has three components that specify logic variables, the body, and the domain restriction. Domain is specified as a Go. Here, we use an empty parenthesis to indicate that we have no restriction on V, and thus, V can be anything. Here, this query asks whether for all the V on the whole domain, if all the V equals to themselves. For the implication, it is a Go constructor with two components, antecedent Go and consequent Goes. This query asks whether A equals 3 implies A not equal to 4. The motivation of these two new Go constructors is that they can serve as a step towards synthesizing programs from specification using universal quantifiers and implication. For example, we want to synthesize a sorting function. We can do that in two ways. In the first approach, we query for a program that for every list as input, the evaluate on the program applies to the input can lead to a sorted version of the input. Then, if the query can be run successfully, the resulting program is the sorting function. Note that the exists keyword is just an alias of the fresh keyword. In the second approach, we query the proposition that there's a permuted and sorted list L2 corresponding to every given list L. On the Curry-Howard correspondence, the proof term for this proposition is a program that does the sorting. Sadly, both synthesizing tasks are currently impractical due to the performance. Then, what can be done? Let's start with something simple. In the first example, we query for two logical variables, A and B, such that for every value in the domain, the value is either equal to A or not equal to B. Our system can successfully retrieve a solution A equals B. To understand how our system solved this query under the hood, we will first illustrate the sketch of the algorithm, and after that, we'll trace this example manually. These are the four main components of our algorithm. The first step serves as a base case. It checks if the domain can be satisfied at all. If not, then the for all Go is vacuously true. Second, if the domain is satisfiable, then we need to check if there's any V at all that can satisfy the goal. We call this step candidate extraction. We do this by directly running the body and consider the quantified variable as existential variable. If we don't get any result back, we know that the for all Go fails. However, if we do get a state back, then the returning state describes the value of V's on which the goal succeeds. But what about the rest of V's? The key insight of this third step is that we can derive a goal that describes the rest of V. We call this new goal relative complement of a state. Once we have this goal, we can run a modified for all goal with this restricted domain, and thus recursion back to step 1. Graphically, we use this arrow box to represent the space of possible values of V. The state we get from candidate extraction tells us the subset of the domain where the goal holds. The relative complement is a goal representing this blue area. We'll show a concrete example in the next few slides. Finally, another way to satisfy this for all goal that isn't covered by step 1, 2, 3 is that sometimes we can falsify the domain by cleverly setting our logic variables. For example, this for all V equals to A, V not equal to B goal can succeed vacuously by setting A equals to B. This is called relative negation in the paper, and we won't go into details in the talk about it. Now let's compute this example, where we query for A and B such that for every value on the domain, the value is either equal to A or not equal to B. Starting at step 1, the domain is clearly not vacuous, so we have more work to do. Going to step 2, we check if there's some V for which the body goal holds. It turns out yes, and we could potentially get 2 states back. And let's say the first resulting state is V not equal to B. Then in step 3, we check if the goal holds for the remaining part of V, or in other words, any V for which V not equal to B is not true. That is, the goal V equals to B. Thus, we run another for all goal, but this time with the restricted domain V equals to B. Notice that we will run this new for all goal with a modified state from step 2. We'll only keep the information on the logic variables outside of the for all goal in the new state. In this example, we'll have an empty state. Now, we try to solve this new for all goal using empty state. Step 1 and step 2 is done in a similar fashion as the last recursion. After step 2, we get a state conjunction V equals to B, V equals to A as the final state. However, on step 3, the other choices of V will be different. This time, it's not simply a negation of the given state from step 2. Since this state also has the equality information between A and B, the remaining part of V should also have this information. Thus, the new for all domain is the old domain conjuncted with the new relative complement that also includes the information A equals to B. What's more, for this new for all goal, we still run with the modified state from step 2. This time, after restricting the information into A and B, we get the state A equals to B. Now, look at this new domain. It's actually unsatisfiable and will fail in the step 1 of the next iteration. Thus, we get a solution A equals to B. This is the end of our example. This delicately designed algorithm seems kind of ad hoc, but it is actually generated from this given proposition. The full details of the proof is in the paper. Now, let's shift our focus to implication. An implication goal has 2 components, the antecedent goal and the consequent goal. In this example, we query whether A equals 3 implies A not equal to 4. To solve an implication goal, we use a combination of semantic solving and syntactic solving. We use semantic solving when the antecedent goal can be easily negated, and so we can rewrite the implication into a disjunction. Then we can reuse miniKanren's existing facility to solve this disjunction. The queries that can be purely solved by semantic solving is a goal that only consists of primitive constraints. Primitive constraints are the equalities, inequalities, and the type constraints, and thus negatable. In this example, A equals 3 is a primitive constraint, and thus semantic solving can alter the implication into a disjunction. While syntactic solving can be roughly considered as purely doing syntactic pattern matching, so it is used for reasoning about user-defined relations. In this example, when assume evaluate 3, if we want to resolve evaluate B, we will unify B with 3. Thus, for an implication goal with both primitive constraint and user-defined relation inside the antecedent, we need to combine these 2 approaches. To achieve a working algorithm combining these 2, we need to take care of the following things. First, we need to accompany the solving computation with a list of goals, indicating the current assumptions, so that when a target goal is a user-defined relation, we can invoke a computation to do pattern matching. For people who are familiar with miniKanren internals, we essentially change the interface of parse function, allowing it to take a new parameter, assumptions. Second, we'll extract user-defined relations in the antecedent into the assumption data structure. Third, we extract primitive constraints into the state instead of putting them into the assumption data structures because pattern matching on them won't be fruitful. Here we trace this small example. We use an arbitrary user-defined relation role and omit its definition. Currently, we don't need the definition, and you will see the reason later. This query asks if we assume that both A equals 1 and row A5 are true, whether that implies row AB. To extract as many primitive constraints as possible into the state, we partition the antecedent into a conjunction of two parts. We make sure the first part is full of primitive constraints. Thus, it is possible that the first part will be vacuously empty. Then we will have the first part as trivial goal top. In our example, the first part is A equals 1, and the second part is row A5. After we find out the two parts, then we invoke three ways to solve the implication. The first two streams tries to falsify the antecedent. The third stream is really solving the goal. Because the first part contains only primitive constraints, taking negation on it is possible. In our example, the first stream is the goal A not equals to 1. Because the second part is not easily negatable, so we conjunct with the information assuming that the first part already hold, and then use implication in the failure goal bottom to falsify the second part of the antecedent. The third stream is the one really does the solving, thus is only different from the second stream in the consequent goal, row AB. This is the big picture of our algorithm. In our example, the first stream, A not equal to 1, is directly solved by using original miniKanren facility. This is a part of a semantic solving in this blue graph, and pointed out here. The highlight plus is the part doing partition of the three streams from the last slide, and this is also a part of semantic solving. However, to really solve the second and the third streams, we need the syntactic solving, which is the green part. Now, we look at how our syntactic solving is dealing with the third stream. In the third stream, we'll directly solve first conjunct by semantic solving, and thus incorporate the information of A equals to 1 into the state. Then we put row A5 into the assumptions. At this stage, we can choose to use pattern matching between row A5 and row AB and directly unify B with 5 to get one solution. Notice that in this example, we don't actually have to look at the definition for row at all, but this is not always the case. Let's look at another example where pattern matching is not enough, and we need to know and unfold the definitions of the user-defined relations. In this example, foo and bar are defined recursively. Foo-z is defined as simply expanding to foo cons 1z, and bar-z is defined as foo-z. If we don't look at the relation definitions at all, we are stuck here. So instead, we try to unfold the antecedent and consequent one time. We will get implies foo cos 1 to foo cos x2. Then pattern matching will easily figure out a solution that maps x to 1. Now, we run some examples in our system. The first series of examples are doing some simple proving. Our system is able to prove or disapprove some simple queries about universal quantifiers and implication with the appearances of logic variables. The first query is looking for a Q such that all value in the domain is not equal to that Q. We expect this query has no solution. In the second example, we query for two logic variables, A and B, such that for every value in the domain, the value is either equal to A or not equal to B. This example is returning one solution. Every solution will have two parts. Here, the first part of the solution is indicating the value of the queried A and B are equal to each other. The second part is a single top, indicating we have no extra constraints. In this example, we query for Q such that Q is not equal to any pair of 1 and an arbitrary X. This is a good example showing how the extra constraint looks like. This query is returning 4 solutions. Here, for each solution, we have an extra constraint. The first solution saying any number, symbol, or string is not equal to that pair. And the third solution saying that if the first element is not 1, then any pair is not equal to that pair. In the above three examples, our system successfully proved some queries reasoning about primitive constraints, pairs, and universal quantifiers. Now, let's look at a second group of examples, graph reachability and game winning. These examples are from Constructive Negation by Evgeny Moisenko from 2 years ago. We find the graph reachability example very helpful to illustrate using implication in the bottom to encode negation in our system. Here, we use this edge relation to encode the graph information. The graph has 4 nodes, A, B, C, D, and 4 edges. We define reachability as usual and define unreachability by negating reachability relation. We use implication and a failure goal bottom to encode negation. Now we can run some simple queries about the graph. The first query is asking for a node that is unreachable from C. The returning answer is saying as long as the node is not COD, it is unreachable from C. That means A and B are the nodes unreachable from C. Here, we will have an inequality constraint instead of equality constraint in the solution because we didn't restrict the domain of the nodes into A, B, C, D. The second query is asking for a node that cannot reach C. Here, our solution says D cannot reach C. We also adopt the game-winning examples from the same paper. The example is interesting because it defines a recursive relation that interplays with negation. We use the same directed graph here. But here, we define a game on this graph. Each node of the graph can be either a winning node or a losing node. If one node has 0 fanout, then it's a losing node. And nodes with edges pointing to a losing node is a winning node. This is how we define winning relation. Winning requires the existence of a losing adjacent node, compared to how the paper requires an extra annotation as stratification when negation is applied to a recursive relation. Here, we don't have such syntactic restriction. This gives us a better user interface. We can query whether C is a winning node and if D is a winning node. However, we don't expect winning A or winning B can succeed or even halt. These two queries don't halt simply because the game doesn't specify them. We know in this graph D is a losing node and thus C is a winning node, but this game doesn't tell us a node without any adjacent losing node is whether winning or losing. Computationally, we cannot conclude anything here. However, if we assume A is a losing node, then we can conclude B is a winning node. This serves as an interesting example from using implication. The third series of examples are all about sorting. Sorting is a basic synthesizing task. However, we cannot really synthesize anything about sorting in the current stage. Our system can only try to prove some basic property. We will make a simple relational insertion sort for booleans. This insertion sort, while given a list, will try to lift all the false in the front. Notice that all our query here will work on lists of fixed lengths. The reason is that we don't have induction reasoning in our system yet to handle lists of arbitrary lengths. It's the best we can do now. This first query is asking whether a list ending with false will sort to the same thing. We know it is not true when X is actually true. The second query is asking whether the negation of the above is true. It should be. We can notice that with just a simple negation, there will be an exaggerated time difference. This difference will be excessively amplified when we are dealing with lists of length 3 or 4. For those cases, the query won't finish in 30 seconds. The good thing is that we still can run some of the following simple queries. These two queries are asking the similar things as the above two, but with lists of different lengths and content. Now, we show the classical miniKanren example, the relational interpreter eval. In this example, we want to show our system can reason about potentially non-terminating program. This is an interpreter for simple Lisp. Variables in this language are represented namelessly using the Brown indices. Then we encode the classical omega function in this untyped language. This IDF is exactly the identity function. Now, in this example, We use implication to encode a false assumption that the unhalting omega can evaluate it to the identity function. Doing so, evaluate on omega can halt and give identity function back as a final result. Because the only possible terminating routine is to rewrite the result of the evaluate on omega into identity function, it is unsurprising to see all 4 solutions are identity function as result. The final examples are about constructivity. Our system is using constructive reasoning because first, all of the primitive constraints are decidable, and second, the disjunction is reasoned by proving at least one of the branch. Finally, we can consider the implication as constructing a new proof given an old proof from the assumption. That is a lambda term. This looks exactly like BHK interpretation. Now we define 2 new relations, a dead loop relation and a halter relation. A halter relation is asking if the evaluate of a given expression ends up with some value. That means the given expression will halt. Let's see what we can do about this user-defined relation. A good example is the law of the excluded middle, LEM. LEM is generally not provable in intuitionistic logic. The first query is asking if, for arbitrary x, disjunction of negation of loop x and loop x hold. This second query replaces the loop with halter. We know the second query won't be solvable in intuitionistic logic because otherwise we'll have a working algorithm solving halting problem. If we put these 2 queries into our system, the system simply unhalt. However, we can run the intuitionistic encoding of LEM using loop. The intuitionistic encoding of LEM can be considered as putting double negation in the front. Here, we push a negation into the quantifier. Theoretically, we can use halter to replace loop here, but this example would take too long for a demo. Finally, we want to emphasize the reason we prefer constructivity here. Ultimately, constructivity makes the proof certificate equipped with computational content. This transforms proof searching of a logic query into a program synthesis of a specification. This provides another flavor of program synthesis. We end our presentation with a discussion on the future work. Currently, our system only focuses on expressiveness and correctness of the algorithm. It is not efficient at all, and we expect a lot of optimization to be done here. Second, our correctness is ensured by a pen and paper proof, but it's not convincing evidence that our implementation is correct. To approach that, we can either generate proof certificate and come up with a proof checking algorithm, or we should simplify our current complicated implementation. The good thing about proof certificate is that it is helpful for our big picture on the Curry-Howard correspondence. To synthesize provably correct program from specification using universal quantifiers and implication. Thanks for tuning in. We hope you learned something from this talk. Feel free to talk about your questions and comments. Thank you very much.
All right, thanks, Indy. So we have a question already from Alexander. Maybe we could bring him on.
Yeah, I can see the question now. So I'll just read the question. I think
Alex is coming.
The not for all xpx is the same as exists x not px. We don't get the same performance both ways. The deep reason we haven't really looked into deep reason, but it's definitely related to how P is defined. In our context, when P is defining a very in a large, like when P is defining a very complicated relation, the interleaving of the relation will cause some effect on the performance. You can see already in the example we ran. So when we replace the loop with halter, the interleaving of the halter will disrupt the correct search and the correct proof, the searching of the correct proof. So it will makes the whole thing slow down a lot.
All right, thank you. Thank you.
Yeah, the next question is, does the approach work with these equalities? Yes, it works with these equalities. So in our context, our miniKanren is working on the functionalized miniKanren that is already equipped with the equality, this equality, and the type constraint. The type constraints is actually the symbol O, number O, and string O. And yet, Boolean is not primitive type constraint. We use equality constraint of true and false to encode that. And these are the basic material, the vanilla miniKanren we are working on. And then we add the implication and the universal quantifier into it.
Thank you. I just asked because we in one of our works on relational synthesis, we suspect that we would need a universal quantification which would work with the equality. So perhaps we can communicate a little more in order to apply your techniques to our problems. Thank you.
Thank you.
So I have a related question to that. What is it possible to characterize the kinds of constraints that the approach can work with? What has to be true about the class of constraints in order to make it work here?
So yeah, that's a very good question. So I did some work into that part in the appendix of the paper. So the way I prove the whole thing is that I axiomatized a bunch of stuff and then I can prove it. So the part I axiomatized is, I think, is a good characteristic, but I cannot really interpret those axiomatization very intuitively. It's like, so I have a feeling that when we are working on a natural number, like when there are natural number, just start with 0 and 1, 2, 3, 4, something like that, and I add a smaller relation into it, the thing will collapse, because when you ask x less than 1, it will need to synthesize x is equal to 0 at x equals to 0, some information like that. And those kind of information is not really works well with our current technique, the relative complement and the other stuff. But yeah, I'm not sure how fixable that is, but it's not really a general framework. It has some limitation, but I haven't looked into that very detailedly.
But the key thing is you're able to construct the relative complement of a domain, it sounds like.
Yeah, that's the key part.
Okay. So I had a little bit of trouble understanding the example with Avalo in your talk with Omega. So it makes sense to me that the implication overall, because Omega doesn't actually evaluate to the identity function, the implication should be true for any program that you might evaluate in the consequent, right? Because the condition of the implication is just false.
Yes, because because the assumption is false, so it should be. So we should synthesize something. In that case, we should result to some result. Evaluate should give us back some result.
But it looks like right now you can handle specifically that case where you can construct specifically certain terms using the syntactic matching, but not other arbitrary terms that wouldn't syntactically match. Is that right?
Yeah, the current Evalo has, our current approach is not good enough. So we have some example that the Evalo, if the condition is Evalo of a pair into a pair, it cannot really deconstruct the pair back. It cannot extract information back from the condition Evalo. it's not very good technique of analyzing the implementation. If that was what you're asking.
I think more specifically, he's asking, since the assumption is false, you should be able to prove anything in the consequent, right? So, but in general, the issue is that we can't always tell that the assumption is false. So it's especially when dealing with a relational interpreter. A lot of things.
Here I wouldn't expect you could, because you can't. If you don't have induction, you can't prove that it definitely won't terminate, right?
Right. So in general, even if you have something that is false, there's no guarantee that we can prove anything in the consequent.
Right. But would you end up in that example? I don't remember. Would you, if you did a run star, would you non-terminate, or would you terminate with a finite number of answers?
I think it won't terminate in that example.
Okay. So that's cool. That captures the fact that you can't prove that there aren't others. Do you have any idea of how you might attack induction?
So the initial proposition by Greg was adding the Leibniz just adding an induction proposition into our mechanically. But I expect that would be very inefficient, because currently our implementation is already very inefficient. So yeah, it's not really. Yeah. So if you
Yeah, as far as the expressiveness, you can put induction axioms in the assumption of an implication, but yeah, the performance might be really bad.
Okay, that's interesting that you could at least already express it. Cool. All right, well, thank you. I think that's the end of our current session. So we have a break in the lounge for half an hour. So please meet us over there. And then we have the second keynote of the day in half an hour after that. So I'll see you all in the lounge.
Okay, we'll be starting again in a few minutes. Just give some time for people to come back in.
So I just pasted the YouTube live stream link again in case you want to share that with your colleagues. I know some people from University of Toronto, they're watching the live stream.
All right, I guess we can get started. So welcome to the afternoon session of the miniKanren workshop. Up next, we have a keynote by Chris Martins, and after that, we will have our last paper on relational floating point arithmetic. So let me introduce you to Chris Martins. So Chris is an assistant professor at North Carolina State University, where they direct the Poem Lab. And the research applies programming languages and logic to interactive media, particularly those which could benefit from procedural content generation, such as games, interactive fiction, and various system simulations. And we're very fortunate to have Chris presenting today on relational content generation. So why don't you take it away, Chris?
Thanks very much, Greg. I appreciate it. And thank you for inviting me to speak here. I'm excited to talk to everybody. Let's do the screen sharing thing. All right, so the title of this talk is a bit of a pun. Often this, as Greg mentioned in his introduction, one of the things that I work on is procedural content generation. And sometimes, but not always, that field of study is kind of situated within environments where people are mostly using procedural programming languages. So I'm calling this talk Relational Content Generation to talk about how relational programming languages can maybe address some of the issues that come up in that world. Yeah, and I'm actually, I want to be upfront about the fact that I am not a miniKanren expert. I have used miniKanren a bit with heavy guidance from Will Bird and another person who had more experience than I did to implement some ideas that I had been working on previously. But I am mainly going to talk about the sort of some other models of relational programming that I'm a bit more familiar with. And I'd be very interested in kind of hearing from this crowd about, kind of which of these ideas might be well supported by miniKanren, which of them might, basically I just want to try to encourage you to kind of think about whether miniKanren might support some of the things that I'm discussing here. So hello, everybody. I'm Chris. I'm an assistant professor in computer science at NC State University. My pronouns are they, them, and my research centers around what many people call game artificial intelligence, including applications in interactive narrative. And in particular, my group tries to research and build tools and small languages, usually domain-specific languages for system design and computational creativity in these interactive media contexts. So I'm also an aficionado of functional programming and logic programming. I grew up with those things, so to speak, in grad school. That was my focus. And I also just am constantly fascinated by how humans work, especially when humans are interacting with computers. So, to some extent, my research overlaps with human-computer interaction. And because of that, I've had to learn a lot, and I've enjoyed learning a lot about kind of human cognition and psychology and kind of how the particular ways that different modes of programming or thinking or interacting with a system can get us to think about and solve problems differently. So this idea of procedural content generation goes back, at least in terms of the origin of the term, to the sort of early days of video games in the 1980s. Originally, it was kind of used as a mechanism for creating a smaller memory footprint of your game. So rather than, basically the idea is that rather than wanting to manually encode everything about your game world, every individual room and asset and piece of decoration and terrain and planets you might visit if you're in a space simulator or something, like rather than trying to hand author all of that content, you set up some basic rules for what types of content can exist, and you implement an algorithm to generate that content for you. this is is a strategy that was used to kind of reduce a memory footprint for older games that couldn't use a lot of memory, but could lean more on processing power to generate those kinds of things on the fly. It is still used today in strategy games. Like Hoplite and Polytopia are a couple of examples that I've played on my phone recently that are like strategy games with procedurally generated maps. People generate sort of interiors of spaces that you can navigate, and levels for games in the class of games known as roguelikes, based on the 1970s game Rogue, which are games where you are traversing a series of dungeons, but whenever you die, you have to start at the beginning. So you need variation in order to make that a tolerable play experience. And then all the way from games like that are strictly text-based or ASCII-based, and to like full high-budget AAA style games like No Man's Sky. This idea has really kind of been permeating the world of games, or at least the kind of like vision that people have for what a good game can be, for the entire history of digital games. It's also not necessarily just about digital games. There's so this is on the left. There's the Spore creature creator from the EA game Spore, which is a game, but it's the kind of the procedural content generation, or an element of procedural content generation that showed up in Spore was the creature creator, which was more like a tool that players could interact with to design the next evolution of their creatures as they kind of go through the stages of evolution. And then kind of based on the way that they sculpt that creature, it moves around in the world differently. It might have a higher or lower chance of survival in the environment that it's placed in. Similarly, in the arts, people have been using very similar techniques to those found in procedural content generation to do things like generating furniture or rug patterns, or jewelry. Sometimes just for the novelty of it, and people will sell these items or will show them at exhibits, but sometimes for very practical purposes, like you may need some kind of modular design for your architecture in order to get a 3D model that's going to work in a variety of different contexts. There's a whole game jam, or I guess maybe software jam, sort of dedicated to this idea that dozens of people participate in every time it happens, called Proc Jam. And I love the tagline for this, make something that makes something, because that's kind of, I would say, like the underlying ethos of a lot of procedural content generation work is like that, each PCG project is kind of building an engine that can generate a possibility space of content. And you get a huge amount of variety from things like this. You get people generating pixelated brutalist architecture to hilarious fantasy names, to abstract silhouettes of landscapes, to psychedelically colored kaleidoscopes, to 3D models of pieces of fruit, right? And so you end up seeing just a lot of creativity emerge from this space that really wouldn't be possible without the help of algorithms. So why do people do this? We mentioned in the beginning that one of the original reasons was to reduce the memory footprint of games, but since the origin of Rogue and the sort of roguelike genre, there's also been a lot of emphasis on this idea of replayability, that a player should be able to have more experiences with the same mechanics of the game, but not have to play through the same environments or the same levels each time. Because if they did that, they might, it would be a different kind of game, because you'd be able to memorize the layout and the sort of specific sequence of actions that you could take, rather than learning more general strategies that can apply in any generated environment. The same idea can kind of extend to not just replayability, which is kind of infinite time playing the game, but also infinite space. Like in No Man's Sky, I think one of their kind of ways of phrasing this was that like space is infinite, so you can explore out in any direction and find a procedurally generated planet, and it will be like fully inhabited with fauna and flora and terrain and all of this stuff. To some extent, procedural content generation is also done to save manual authoring effort. You certainly don't need as much hand-authored content when you have a procedural algorithm for generating it. But that said, that's sometimes a bit of a trap, because once you start implementing a procedural generation algorithm, that can take more time than it might have taken you to author the equivalent amount of content by hand. But if you're doing, if you're generating infinite content, obviously that's not the case. And then finally, one of the most important reasons that people embrace PCG to me is augmenting human creativity. The idea that algorithms are, fundamentally, like, even if we're implementing the algorithms, like, they are going to produce content in a way that doesn't exactly resemble or mimic the way that we would do it if we were trying to come up with ideas on our own, whether that's through randomness or through, sort of recombination of the way that the algorithm works. And this idea of augmenting human creativity also makes PCG really nice to fit in with this idea of mixed initiative systems, which is a lot of where the work in my lab is focused, is on kind of creating these tools that people can use to create things, but the tool itself, is also doing some of that creative work and operates more as a creative partner with the human creator. So there might be some elements of your map that you want to design by hand, but other parts of it that either you're not sure about, or you at least want to get some kind of computational feedback about what this design is going to result in terms of player experience. And mixed initiative tools are things that can kind of show you your current design and give you some analysis of metrics that you care about for that design, and also propose possible alternatives. This is a screenshot of the Sentient Sketchbook tool for designing StarCraft-like strategy map games. So the question here is, that kind of frames much of the work I'm going to talk about, is how can relational programming augment creative practitioners' ability to define and navigate possibility spaces, which is what I argue anybody who's building a procedural generation system is doing. They're defining they're trying to define and navigate a possibility space of content. So to talk about that, I need to get into a little bit more about what PCG is all about and what the goals are. So some of my colleagues in this space wrote a free book online called the PCG book. And in the introduction to that book, they define a few desirable properties of generators. And of course, what you want out of your generator will depend on the context and the situation you're going to use it in. But some of the things you might want are speed, reliability, controllability, expressivity and diversity, and creativity and believability. Speed is fairly self-explanatory. If your generator is running in real time, if it's something where the actions of the player are going to feed into or determine somehow the results of the generator, then you need to be able to generate on the fly and not cause the player to wait for a long time. Reliability basically means, can you always depend on the generator producing valid content that's playable? Or an unreliable generator might produce a lot of things that are basically garbage, but if you're doing that offline and you have the ability to curate or hand select examples, then you may not need as reliable of a generator. Controllability kind of refers to how much dependency do you want there to be on the input space. So do you need to be able to specify, parameters that are going to change the possibility space? Do you need to be able to take a stream of player actions and feed that into your generator? Or is it something more generic where whatever, it's just a level that's generated randomly each time? Expressivity and diversity kind of refers to how many things are there in your generative space and how different from each other are they. This was actually kind of a common criticism of No Man's Sky, is that even though it's supposedly like every planet is fully populated and procedurally generated, they were kind of all like, they all had the same feel to them, and they all had a, sort of a character that was difficult to tell, like, okay, well, these things are different from the last planet, but why does that matter? Or what's the, what's the content, what's the actual meaning of this variation? How does it affect my experience? And then finally, creativity and believability is about, kind of whether the content that's produced is sort of satisfying from the perspective of whoever the intended audience is, whether it seems to be a creative work of art or a believable line of dialogue from a virtual character, for example. PCG strategies are many. Some of them include directed randomness, recombination, generate and test, and search. Directed randomness is the kind of thing that you see in analog procedural generation as well. So before we had computers, there were artists who were using algorithms and, kind of like rolling dice and using other forms of randomness to kind of dictate, and following rules to dictate like the lines that they would draw on a page, and kind of they would execute the algorithm, but they were still creating art algorithmically. This is an example from Kenneth Martin called Chance and Order from 1951. And then there are also things like for Dungeons and Dragons, which is a tabletop game that you don't usually play with a computer. There were these sets of so-called dungeon geomorphs, or tiles, that you could use to kind of arbitrarily place them next to each other in a tile grid and create an arbitrary dungeon. So those are examples of directed randomness and recombination. Sometimes the techniques of directed randomness and recombination are referred to as additive, because they're ways of sort of strictly populating the generative space of you define a set of rules, and that says, here are the things, if you think about induction as being, I can talk to math geeks here, so I can say, like, if you think about induction as being a least upper bound on kind of extrapolating a set of rules, you can also think of additive procedural content generation this way, in that you're defining a set of rules, and then it's kind of taking the limit of that and populating a possibility space with all of those things. Things like generate and test and search are more are sometimes referred to as subtractive, because these are ways of saying what you don't want in the generative space. They're ways of saying, I have an evaluation function, or I have a way of testing for validity of this content, and I will rule it out under certain circumstances. And then search, like going through a search space and saying, like, okay, I'm not going to go down certain branches, I'm going to prune my search space, is also kind of subtractive in that sense. So one of the most commonly cited ways of doing additive procedural content generation in a way that's nonetheless, I think, fairly declarative in nature is basically using variants of context-free grammars. So these are several examples of how you can use context-free grammars to do generation. In the upper right, you have an example of an L system, or a Lindenmayer system, which actually originated in biology and was inspired by the way that leaves place their leaf growth. And so you basically define an amount of length for each segment and an angle to turn, and then you write a production grammar for little turtle programs, basically Logo programs that like say, okay, go forward and then turn left by whatever the angle is, and then draw a line, and then turn right, and then draw a line. It uses the square brackets to as push and pop symbols as well. So you can do a little bit of it also, I guess it's not technically as well, it's a CFG that generates this, but then it also can like save its space as it's executing. So Lindenmayer systems are notably used to generate like things that look like vegetation or trees, and this is implemented in the tool SpeedTree, which is an industrially used engine for terrain generation in games. Other examples include grammars that can generate the layout of maps or dungeon levels in a game, or even like a little bit more concretely, things like shape grammars, where you can describe how an initial shape You can provide production rules basically that turn an initial shape into something more, complex that's composed of self-similar things, and then those can recursively unfold to create these sort of two-dimensional or three-dimensional structures. The lower right screenshot is a game called Unexplored, which was made by someone who's published papers on basically using these like dungeon level layout grammars in a commercial game setting. Evolutionary algorithms are well, I think for a long time were kind of like one of the dominant methods of procedural content generation. And again, not just in games. There was an interesting project that was active for a while called PickBreeder, which basically took these like essentially random noise images and put them on a web page for people to vote for. So evolutionary algorithms are kind of a simulation of something that is a little bit like biological evolution, in the sense that you call a population down to those that are closest to whatever it is you're looking for, which is defined by an evaluation function. And then you sort of, it introduces an element of randomness into the search, usually through something kind of like mutation. And then whatever the top, n members of the population are, you do crossover and mutation, generate new members of that set. And keep going basically until you find things that pass the threshold of the evaluation function. And they did this with basically using humans as the evaluation function. So humans would sort of select the images that looked closest to particular tags that they were interested in. And they would gradually sort of evolve these random shapes into things that look more like real life objects. In the games world, there's a really cool project from Cameron Brown. Also interesting to PL people, I think, because he defines a domain-specific description language called LUDI for describing board games, sort of two-player competitive board games. And he uses an evolutionary algorithm to generate them, to generate sets of rules for new, interesting board games that are going to be fun to play according to various metrics that he defined computationally. And so he has this nice diagram of kind of how this algorithm works, in that you start out with a population, select parents and crossbreed, crossover and mutate. And then there's like this series of checks, right? Where like, because evolutionary algorithms don't tend to like necessarily obey things like syntax, especially if you have like some weird crossover function that's gonna do something unusual to the syntax, then like you might wind up with something that's not well formed. So if you do that, you have to throw it away. If it is well formed, it may just be that it is too slow, it's not performant, or it just has some other characteristic that you can easily check that doesn't make any sense. Like if this were a program, right, it might be like, does it type check, right? And so you have to go through all of these checks and throw things out if they're not good enough, and then if they are, then they survive into the next round of the population for generation. But all of this is basically just a way of defining and navigating a search space, right? You're kind of saying there's a set of allowable things, in this case, board games of a particular size. There's the set of all of those possible things that might exist, and then there's the set of things that actually conform to some properties that I'm looking for, much like in program synthesis. So there's kind of these two perspectives. I would say that there's kind of a tradition that comes more out of the arts, in terms of if you just want to kind of describe an algorithm for making a thing, often those are described very imperatively. If you take a look at there's a popular tool called Processing for making generative art, that a lot of artists use, because it's a dialect of Java, but it's like nicely documented, and there's a nice user community around it, and so it gets a lot of adoption. But essentially, rather than defining like a data structure that defines the artifact you're trying to generate, you never explicitly write that down, right? You just write like a series of instructions to kind of explain, and sometimes there's randomness, but like to explain kind of step by step what the algorithm should do in order to draw something to the screen. And I think that's in contrast to a sort of more the tradition that's more rooted in games and that's kind of these days more centered in the search-based approach that feels a little bit more declarative, where you're describing a possibility space and then essentially sampling from it. And this is where answer set programming comes in, which is the flavor of relational programming that I'm mostly going to talk about. So answer set programming is a way of doing logic programming where rather than defining a bunch of facts and also providing a query that then gives you an answer or a set of answers, it doesn't give you, so like in miniKanren or in Prolog or something, right? Like an answer takes the form of a mapping from logic variables to ground terms, right? You're generating like basically unification sets. In answer set programming, what you're doing instead is generating sets of so-called stable models. And I'll get into more about what that means. I'm going to motivate it with an example, which is loosely based on biome generation, which is something that like I just kind of got fascinated by for a bit. And it makes a fun example in answer set programming, where like if you're trying to generate a fictional world from scratch and you want to define sort of what types of life grow there, like what types of vegetation and maybe what types of animals are there, then like first you kind of have to figure out what sort of terrain you've got and like how hot and cold it is and how dry and wet it is. And so this is an area that's kind of rife with like interesting sets of constraints and possibilities. So it makes a nice demo for procedural generation. And you're not meant to understand the code on these slides yet, but this is just to kind of show you at like a zoomed out level, like what the input and output is of doing answer set programming. So when you write a logic program, you basically create a thing that looks like, if you blur your eyes, like basically just like an ordinary logic program, and then produces for you a set of answers. So you never explicitly issue a query. You just have your program, and then you say you ask for a certain number of answers, and it gives you a set of predicates, of ground predicates that are essentially consistent with the input program. So we'll build up to that example kind of from first principles, starting out with just sort of a quick primer on how this stable model thing works. So I guess something to understand right off the bat, if this helps you at all, is that answer set programming can be implemented with SAT solvers. And in fact, like I think the most common implementation, Klingo, is actually built on a satisfiability solver. So that's like the same set of things you could do with, for example, like Z3 or any other SAT solver, or are the sorts of problems you can solve with answer set programming. But the way you write it is closer to traditional logic programming. So if you write down a couple of facts, right, like there's an ocean, there's a forest, there's just going to be one answer. That's the set of the set of stable models is one stable model in which there is an ocean and there is a forest. The syntax of curly braces does what's called a choice rule, where you basically say, this thing might be a fact. You can decide whether or not to make it true, as long as that choice is consistent with everything else in the program. So if you say curly braces ocean and curly braces forest, then suddenly there are 4 answers, because now there are 4 stable models that satisfy this program. One of them is the empty model, in which neither of those things happens to be true. One of them is the one in which only ocean is true, only forest is true, and then finally the one where both of them are true. So you can set up implications. You can say choice, curly braces ocean, and then you can say ocean implies forest. And if anybody wants to quickly type in the chat your guess for how many answers there are, if you didn't peek ahead in the slides already, go ahead and type that in. Okay, good. I see a range of answers. That's actually good to see. I think that's yeah, it's good to sort of think through how many things you might expect. Some people are saying 3, some are saying 2, someone said 1. Okay. All right. So yeah, so the answer is 2, right? Whether or not there's an ocean is kind of our one choice, right? So we have just sort of a single branch in our decision tree, and we can either make an ocean or not. And if we do make an ocean, then it will necessarily imply a forest. Forest will have to exist in order to make this a stable model. Now we could put forest in curly braces, and then, you know, even if an ocean exists, we now have a different choice of whether to create forest. So that would be a different program though. So for this one, there are two. There's also this idea called an integrity constraint, which is essentially, you can think of, this is called a headless rule. Sometimes I like to teach answer set programming on Halloween for the puns, because we can talk about headless rules. And so this is, you know, this is a rule where the neck doesn't have anything to the left of it. So it looks very strange. You can think of it as sort of being implies false, right? Rather than implies like something that we would expect over here, it implies nothing. So it's like these two things together are a contradiction. So if you say you have a choice to make it, you can make it wet if you want to, you can make it dry if you want to, but you cannot make it both wet and dry. And then in that case, there would be three possible answers. You've now sort of set up this mutual exclusion between them. And, you know, and then you can build on that. So you can say, all right, you can make it wet or dry. You can't make it both. If it's wet, then there's an ocean. And if it's dry, then there's a forest. And that kind of gets you the same, essentially the same three answers we had before, but, you know, augmented with this additional rule or this additional fact of either wet or dry, whichever the condition was that led to the terrain. And so a natural extension of the choice rule syntax is this idea of having putting a minimum and a maximum. So the number 1 over to the left is a minimum number, and the number 1 over to the right is a maximum number. So here I'm saying there should be exactly one fact of the following form. And so I can start putting in my logic variables and saying, all right, I want there to be a tile in a given area, and it's going to have the value property T tile, so long as the capital T tile is a type of terrain. So this is basically saying assign a terrain to an area, and then do that for each area. So that's what the implication on the outside says. Okay, the syntax is a little bit complex, and I'm not going to fully explain it. It is possible to kind of elaborate this out to just the style of choice rules that we saw before. And in fact, what Klingon does as its way of solving answer set programs is it first totally grounds a program. So you have to, it's another interesting constraint, is like you have to make sure your program is finite in terms of the number of facts that are implied from whatever you start with. Yeah, so this can all like, this is all kind of like syntactic sugar that can elaborate out to that more basic form of choice rule, but essentially you have one fact of this form for each of the thing, you know, for each thing that for which this predicate applies. You can set up integrity constraints to do things like stipulate that perhaps mountains and oceans can't be neighbors. Maybe you only want to generate examples where there's a more gradual sort of variation in the elevation of the terrain. And so you don't want sort of mountains and sea level to be right next to each other. So you can say, if there are two tiles, one of them has a mountain, one of them has the ocean, then they cannot be neighbors. And you can write that with an integrity constraint this way. And then you can also add hard-coded parts of the map yourself. So if you want to say, like the entire top row of my map is ocean, then you can write a regular kind of logic programming rule to say the tile at each of these positions, 0, n for any n in our y range, should be ocean. So this gives you kind of a nice way of both of combining this kind of design of stipulating what is in the map with rules that can kind of fill in the gaps according to constraints. So this is typically your workflow, right? You author your ASP program, you send it out to the solver, which generates a bunch of examples. If you're in some kind of, if you're trying to generate some kind of visual domain like maps, you probably have, you probably need some tool to visualize it for you or something. And then you need to sift through that set of examples, and we'll get into that a bit later. But essentially, then you have a set of examples that you can evaluate. And if you find things that you're like, oh, I actually didn't want maps where like 90% of it was ocean and there was only one land tile, then you can start to refine your idea of what even the specification is that you're trying to generate. And you go back into your program and like stipulate a new constraint. Like you might say, oh, okay, I want it to be the case that like at least this many of my tiles are going to be land tiles. The tools that are available for this kind of thing include Potasco Klingo, which I've been referencing a bit already. It's open source and fairly well maintained. And then more recently, one of my colleagues, Ian Horswell, has developed a tool called CatSat, which has native Unity integration and a bit better support for randomness. That's another interesting thing, is like when you ask for a certain number of answers, you can tell search you can ask it to do search in a random way, but there's not very much control over what that means and what the sample space is that you will get when you ask for a certain number of answers. So CatSat is an implementation that's kind of a little bit more tuned to random sampling and has fairly decent performance for the applications of ASP that are common in procedural content generation. So why is this particular tool good for PCG? Well, let's like revisit some of the properties that we talked about. I will start off just by saying the speed is not a property that I would say answer set programming particularly does well at, and that's mostly because answer set programming is a general purpose tool. It's like general purpose SAT solving. And so while, yes, we do have reasonably well optimized SAT solvers, there's always going to be ways that you can write programs and domains that will essentially have exponential blow up, depending on like the size of the level. And it's not, I have found in my experience teaching ASP and having people use it, having students use it in projects, that while it's possible to optimize ASP programs in terms of clause ordering and so on, and the way that you write your predicates to like speed up, it is very easy to just naively write your program in such a way that you get exponential slowdown that is prohibitive to use in online PCG applications. So that's something that I think is worth like considering. I'll revisit that a bit. But otherwise, I think it does pretty well, right? It's got a good, certainly better reliability than most evolutionary algorithm approaches, wherein you can really only specify what you want kind of indirectly through these evaluation functions, and then hoping that the sort of randomness of the mutation and crossover will get you in a portion of the search space that you're interested in. Whereas in ASP, you can just directly say like, nope, this part of the search space is not valid. You can have you have pretty decent controllability because of the fact that you can just straight up add hard-coded facts. You have pretty good expressivity and diversity through the use of choice rules, and just the fact that it's a logic programming language, you can define whatever terms you want. And of course, creativity and believability. I mean, certainly it's possible to do that or to not do that. It's fairly domain specific, whether or not a given, that's kind of like the job of the implementer, I would say. In this case. In terms of ASP and creativity, I do think that it has two kind of nice, like emergent properties that are good for facilitating this kind of thing. One that I'll refer to as the sculptural approach to design space creation, and one that I'll refer to as bidirectionality. So by sculptural approach, what I mean is that often an answer set program kind of consists of three sections. One part where you generate content with usually with a bunch of choice rules. One where you do sort of some standard logic programming to define whatever properties you want. And then another where you add integrity constraints to kind of chisel away at the space. And I'm using that kind of metaphor deliberately to fit in with the sort of sculptural approach idea. So kind of to go back to our earlier terminology, generating with choice rules is a bit like the additive part of procedural content generation. and constraining things with integrity constraints gradually sort of carves away bits of that search space and is more like the subtractive aspect of content generation. There are two projects from my lab that use answer set programming heavily. One of them is a game generator that we made called Gemini. It generates games, not like, so in Cameron Brown's work, he was generating board games meant to be played kind of between two humans. In our case, we were generating single player kind of arcade style mini games that were designed to fit within the context of an interactive narrative experience. So there would be some sort of story content on the left side of the screen and some sort of abstract mini game on the right-hand side of the screen. And the mini game was supposed to in some way reflect the narrative, which was also being procedurally generated by a different system. And so with our, we implemented a game generator for that using answer set programming. And more recently, I've been looking for a title for this narrative generation engine my student Chinmaya and I have been working on, where we're essentially trying to study problems in internet privacy related to user comprehension and developer comprehension, and we found that there are a lot of situations where people want kind of narrative explanations of privacy policies or example scenarios that they might have to consider. And we're using answer set programming to implement a narrative generation algorithm and do that in a way that can kind of be interacted with and explored. And I have some funding from the NSF to do that. So where bidirectionality shows up, and one example in the Gemini project is that we essentially implement a theory of grounded meaning in games known as proceduralist readings, which is kind of it's similar to how, if you recall, like in your literature class or something, like you would read a poem and then you'd be asked to interpret the poem, right? Like tell you what the poem means, right? The idea is we can kind of do the same thing for games. And we can do that even for abstract games by understanding what the goals of the player are and how the mechanics of the game interact with those goals, and thus what is likely to be an average or like a sort of typical experience that a player might have when trying to reach a certain goal under a set of constraints. And this theory of proceduralist readings was previously published and developed by Ian Bogost and Mike Trainer, and we kind of encoded that whole theory as a logic program. And the idea is that once we encode the theory, we can both use it as a tool for analysis, where we can hard code some rules for a game and then ask it to generate sort of theories or interpretations of that game in terms of its potential meaning. Or we can give it a set of target meanings, a set of target sort of aesthetics or themes that we want to come out through gameplay, and then ask it to generate game mechanics that match those target meanings. So the sort of one direction of this bidirectionality is synthesis in the same sense as program synthesis, right? Like you take a set of constraints and then you are generating examples that meet the constraints. And then the other direction is analysis, where you provide some examples and then it tells you potentially some properties or some metrics or some feedback about those examples. I think that I'm really interested in potentially this being connected to Amina Torlak's concept of solver-aided programming, wherein, essentially, like in that situation, you're primarily interested in analysis and in safety properties of your programs, but there's kind of no reason this couldn't also be more like, you can also be checking for like other sorts of properties in a procedural content generation setting. Other examples that are perhaps more familiar to this crowd include you can use a context-free grammar, both for parsing programs, let's say, or expressions, and for generating things. You can use a context-free grammar to generate text or to generate programs. You can use typing rules that are like inference rules, which are essentially can be written as logic programming rules and clauses. You can use them for type checking, or you can use them to do program synthesis if you have a sort of type-driven program synthesis engine. And in the career project, we have a tool, we have this kind of theory of relating how, how plausible user stories relate to privacy policies. And we can either sort of generate plausible user stories from that, or we can do something like hand encode or automatically translate an action log from someone's interaction with a system, and then kind of audit that for compliance with the privacy policy. And then a final kind of aspect of of answer set programming for PCG that I care about a lot is usability. And this is the kind of thing where, you know, if you hang out in games research crowds, like they're very interdisciplinary, which is a thing that I like about them. But you'll often encounter people who don't have formal training in computer science and who don't, you know, who are not going to be able to sit down with a completely new model of programming if, like, you know, if they learn something like processing, which is just a small, like a sort of subset with some libraries for drawing, and then you sit them down with an answer set program, it's not going to make any sense, right? And so there's often like, you come up against these usability hurdles a lot when you're trying to address or sort of like appeal to creative, audiences of creative practitioners. And I think this is really important. And I try to, in my work, I've been really inspired by Kate Compton's work on she defined this term casual creators to refer to tools that are kind of intrinsically pleasurable to use, and that people use them to create things. Like there's an artifact they create with them, but it's kind of like they do that more because it's fun to use it than because they're interested in becoming a professional maker of that type of artifact, right? So they're engaging with a tool like this casually, in the same sense that a casual gamer might engage with a casual game like while they're waiting in line, or, you know, as a way to kind of fill gaps in their schedule, rather than as something that they're going to sit down and deliberately do and try to invest a ton of learning and time to getting better at. So some of the principles that emerge from this casual creator work, after Kate surveyed a bunch of existing examples that sort of she considered within the space, are instant feedback, the kind of idea of, you know, not having to wait for a full compile cycle in order to see how the change you made an effect on the output. No blank canvas. So the idea of like, there's always something on the screen prompting you about something you could do, rather than just a blank screen where you don't know how to start. Limiting actions to encourage exploration, or the idea that restraint breeds creativity, that if you kind of say, okay, no, you only have like 3 choices for the types of creative decisions you can make here, then that's going to kind of, while it makes it a smaller possibility space, it's at least going to make it a more navigable one. The chorus line, which is the idea of showing lots of examples of possible things you can make kind of on the screen at one time. And then saving and sharing, and I think relatedly hosted communities. So this idea that like, if you let people share what they did with someone else, and also if it's like, if the format of sharing it is itself editable, so people can kind of fork off of each other's work, and do that. I mean, yeah, of course, we know that this is great in like open source and on GitHub, but for non-programmers, it turns out this is great too, like for just creating things that you want to share with the world. And, you know, whether or not that's code, like it's still really nice to be able to see previous examples and build off of other people's work. And then like aspects of the community that encourage like modding and hacking existing examples, as well as good teaching materials, also go a long way for casual creators. So we've tried doing a bit of this work. I think it's a bit of a challenge, and maybe even a mistake for like academia to try to be responsible for, you know, all of these different properties. I don't think that that's necessarily achievable, but I think that there are some of these principles that we can adopt in what we build if we care about usability and inclusivity. And that includes the idea of a structure editor, right? Which appeals to the no blank canvas idea, that rather than having just a blank text editor where you can write a program and you have to go and like read a bunch of documentation to understand what the syntax even is, you have some like widgets or affordances, like a big plus sign that when you click it, it gives you a menu of options. And then you can piece together your program this way with some more prompts and scaffolding around what you're doing. So after we built Gemini, some later students at UC Santa Cruz, including Max Kreminski, started building this tool called Germinate, which is a structure editor for creating design of.
Hi, Chris. Are you there? You, I think you fell offline about a minute ago.
Oh, okay.
Or just under a minute ago.
Any idea what the last thing you heard me say was?
You were talking about Germinate and...
Okay.
Yeah.
Okay, great. I'll start. I'll go back to the slide then. Yeah. So Germinate is designed to embody some of the casual creator principles through.
Oh, I think you need to reshare your screen.
Oh. Thank you. Okay. Everything look good? Can I get a verbal yes? Okay, yes, I see the thumbs up. Yes, good. Thank you. All right. Sorry about that. All right. So casual creators for answer set programming. This is one that we built for the Gemini system to basically to enable people to write down these specifications for their design intentions for games that they could generate, and then when they click the big generate games button, they see a bunch of playable examples, and they can go back and tune their specification if they don't like them. Along similar lines, we've recently been working on a tool for tile map editing based on similar principles, again with a web-based widget sort of structure editor for creating these expressions that represent rules and constraints in the answer set program. So you might want to say that there are at most 4 roads within one space of each other, so that you kind of create roads that look a little bit more like roads and less like big blobs of gray space. You can also you can see these lock symbols on the map, which indicate that you can sort of lock in certain parts of the map that you like, and then let it generate the rest of it. And we're kind of working on trying to figure out what the most important set of features would be for someone who wanted to use this in a real PCG application. And that finally brings me to this idea of navigating possibility spaces, which I think is one of the biggest kind of open problems. There are people who started addressing it, but I think it's still one of the things that needs the most kind of research attention at the moment in terms of mixed initiative PCG tools. So the question is sort of, once you've defined a possibility space, how do you know what's in it? How do you navigate it? I mean, this is the kind of thing that also, of course, shows up anytime you're thinking about a neural network or any machine learning algorithm that's being fed a bunch of data for training, right? If you don't systematically go through and read your data set, you don't necessarily know what's in there, and you don't know what the possibility space of what this thing can produce really is. People have gotten in trouble because of that. CF, Microsoft Tay, right? So you may be one, and this refers a bit to the sort of controllability aspect of PCG, wanting to be able to have a better sense for what things are possible to generate, and also just what the distribution is. Is it going to be the case that most of your content has a certain character to it, and while it's possible to generate content without that character, it's unlikely, right? Relational programs, as you know, tend to have more than one answer. That's great. That's what makes this whole thing possible. But in what order do they show up when you ask for them? In what order does the solver find them? Can you easily reason about the semantics of a program in terms of what order solutions are likely to show up in? Can you control that in any way? Can you say, I want to like ignore this whole branch for now, and you can obviously do that by like adding new rules, but can you do this in some way that is going to be a little bit more granular without necessarily modifying your whole program? And is it possible to even get like kind of a bird's eye view, like sense of the overall character of that possibility space? My colleague Mike Cook describes this as the kind of distinction between a possibility space and a generative space, where the possibility space is like if any of you are familiar with Borges's Library of Babel, right? Like any possible book you can write is going to be in that library, but really you're only interested in books that at least have well-formed sentences, if not probably like plots and characters. Or like paragraphs or some kind of authoring intentionality behind them. So there's a possibility space, which is just the basic representation of all the things that could exist. And then there's the generative space, which is the things that your constraints or evaluation functions or whatnot actually limit your generative space to. And how do you get a sense for what that looks like, right? And so one way of doing this is through something called expressive range, which was introduced by Gillian Smith in 2010 in the context of a platformer level generator, where the basic idea is you define a set of output metrics. In this example, it was the linearity of the level and the difficulty of the level. And then you can group all of the possible outputs that your generator can make in terms of those things and map them onto a two-dimensional, or perhaps I suppose in-dimensional histogram or heat map, kind of showing where your examples tend to cluster, and then visualize that probably as a 2D space by taking those output metrics pairwise and showing it in a diagram like the one on the right here. Something I've wondered, just as a side note, is kind of whether this idea of thinking about expressive range might be applicable to programming languages as well. There's been some exciting work from Mike Cook again on interactive tools for doing this kind of expressive range analysis automatically and allowing you to interact with that possibility space, selecting examples that show up to see what they look like. But fundamentally, I think that there's a kind of a challenge in this space, which is balancing expressive capability and difficulty. The casual creators ethos very much sort of pushes you to the left side of this graph, in which if you are encouraged to, if you have a very, very tiny programming language, and I think miniKanren probably counts as that, right? Like you have, there's only a small number of things that a user has to learn in order to be able to do everything that's possible. And, and that's great. And then at the same time, then you also have examples like tracery, or like a, paint by numbers system, let's say, where I didn't talk about tracery, ignore that. Like a paint by numbers system in which, like, yes, the relative difficulty is going to be low, but you also, if you're following the rules of the system, you can't like just go off and paint anything you want. The whole point is that you're following some rules so that that whatever you're doing is going to be within the bounds of some kind of external notion of what qualifies as a good example of an artifact. And as you try to support people who have kind of more expansive definitions of what sorts of things they want to create, you need more expressive capability. You need to sort of loosen those constraints a bit. But then you often wind up with this so-called extensibility cliff, where like in order to provide someone with the ability to fully customize whatever they're creating, you kind of just like throw your hands up and say, well, all right, you can define your own rules. Or, in miniKanren, this might be like, well, okay, you can use whatever the host language is to define your own things. I don't know if that's really a good analogy because, I don't know, but we can talk about that later. But I think that this is just like fundamentally a tension that anybody who's designing a language or a system for human creativity has to contend with. So I kind of wonder, like, are there opportunities here potentially to, can we think about some of the ideas that we use in domain-specific languages and compilers to maybe do something similar for PCG systems, where answer set programming is a general framework for authoring PCG, but are there sort of domain-specific ideas for different types of things we're trying to generate, like grids of tiles, for example, where we can dramatically prune that search space and maybe get some optimizations and improve the speed of our generator, for example. Are there sort of constraints on different things we should be exposing through these interfaces for, say, editing ASP rules? These are the kinds of questions that I've been thinking about lately. So that's it for me. I know I'm a bit over time, but if there is time for questions, I'd be happy to take them. Thank you.
Yeah, let's answer a bunch of questions. I think it's fine. This is
right.
This is a really good talk. Thank you for coming today.
No worries. Thank you.
So one thing I just remembered, I think you were cut off while describing the idea of no blank canvas.
Okay.
Did you want to elaborate on that a little bit?
Sure. Yeah. Yeah. The no blank canvas principle is essentially that the thing that you're interacting with as a creator should have some kind of affordances. So rather than a blank text editor, for example, it's like a well-established fact in teaching computer science to novices that having something like a block-based language where there's a palette and kind of a catalog of different syntactic constructs that you could put there is really helpful for students who don't even know what they see that there's a blank text editor and they have a keyboard and they could type any string they wanted to, but only some, they don't have a mental model for what the syntax tree of the language is, right? So similarly, when you're in casual creators, if you're trying to create an artifact, giving someone kind of some scaffolding to say, this is the type of thing you might make. If it's a table, right? It probably has a flat surface and some legs. Let's start there and kind of give people some prompts to build on rather than just assuming that they know right off the bat how they should scaffold their own creation experience.
Yeah, that definitely makes sense. So it looks like we already have a question from Alexander. I'm going to show it.
Cool.
So let's see.
Yeah.
Let me see if Alexander wants to come to the stage and talk about this.
Do you want to say your question aloud?
Yeah, sure. So programming language buggers look like they have some similarities to this. When I used one, I got some extremely varied links on the output, and I got sometimes three I don't know, argument programs, and then sometimes 2-page programs. Is this an output for relational generation as well?
Yeah, I think it is. I mean, particularly if you don't. So I think a lot of people. It's interesting because I feel like if you were working in a level generation space, one of the most common, very first things we do is we define the dimensions of the thing that we are generating, and we might want some variability on that eventually. But I think typically we're okay, first I want to see if this thing can generate 4x4 grids of tiles, let's say, and just start with a really small kind of size and then only generate things in that range at first, and then slowly grow it to have a slightly bigger range of possible sizes. So, I mean, maybe that, I don't know if approaches like that are similar in program fuzzing, but I guess, yes, the same problem absolutely can happen if you don't kind of stipulate those constraints up front.
All right, thank you.
I would actually assume typically based on the search order of answer set programming, by default, we would get short, answers that were too short or, shorter than we wanted, rather than longer than we wanted.
Anyone else have questions? I have a few if nobody else does. Oh, looks like another question appeared. From Michael Ballantyne. Oops.
Hello, you want to come on stage?
I think it's bringing him up. This software. Not happy with error meet.
I think I see Michael down at the bottom.
Oh, okay, good. Finally.
It might just be taking a bit.
Yeah.
Michael, I think I see you, but I don't hear you.
Oh, okay.
All right, now I hear you.
I think I have arrived. My laptop is struggling with AirMeet. It sounds like it's lifting off. Anyway, I was wondering the privacy policy story example that you gave. To me, it sounds sort of like you might have a language of describing privacy policies, and it kind of reminds me of the way we use relational interpreters to be able to interpret a language in a relational way. So I was wondering how you relate those programs to ASP, whether you compile them or you have to manually encode, or what kind of thing you do.
Interestingly, we don't really have a DSL. Well, yeah, I guess we sort of have a DSL in the sense that we're encoding. We implemented a planner inside of ASP, specifically a narrative planner. So it kind of has a PDDL, like, if you're familiar with that at all, like a planning domain definition language. It has a way of describing actions with preconditions and effects. Is the short of it. And yeah, and similarly, actually, in the Gemini project, like, we kind of came up with a domain-specific language for describing game rules along the similar lines to how Cameron Brown did for the Ludi system. And so, yes, this like idea of sometimes we're writing DSLs within our relational system and trying to then write relational programs over that does seem connected, perhaps, to the idea of relational interpreters, but I don't think I know enough to necessarily say more about that. But yeah, I think we are doing something similar.
I guess I was thinking specifically about the directionality example you gave, of that you could generate user stories from rules, but you could also, for example, audit an action log according to the rules.
Right.
And then a third thing it seems like you could do would be to derive a set of rules from a log of actions that were legal or forbidden, would be the sort of full interpretive mode of that.
Yeah, I think in order to derive the set of rules from the actions, so that type of task I would characterize more as being related to inductive logic programming, of kind of being able to take a set of examples and then generate rules that could have produced those examples. I think so, because we're kind of encoding privacy policies right now directly, like as logic programs in ASP, or sort of like as constraints over the set of possible stories you can tell. We don't have a DSL for describing privacy policies, I guess I should say.
I see. Okay, now it makes sense.
That part would be a challenge, yeah, or we would have to do that a different way.
Right. Okay, cool.
Yeah, thanks for the question. That's a cool idea.
So I have one on touching on what you mentioned about how you need the program to be finite, or the state to be finite, to be expressible in ASP. Is there a way to tackle unbounded game worlds through some kind of finite representation that grows, maybe? Or
yeah, encoding infinite data structures is one of my perpetual struggles with ASP. Because I keep trying to use it to encode like either like natural languages or programming languages, and and generate expressions in those. And of course, that's like those are infinite data structures, and even just like lists, right? Like that's a little bit challenging for ASP. There are some encoding techniques, some sort of tricks to it. Most of which involve like specifying a bound of up to which you'll search. But some of those are really, really slow, and some of them are less slow. And it's like sort of challenging to get, like the ones that are actually performant are like require rewriting your logic program in a more substantial way. So it can be frustrating sometimes.
Thanks, that makes sense. something you mentioned about additive versus subtractiveness, and then you described how the different types of rules in ASP are either additive or subtractive. Is there also an analogy in terms of the search order of a logic programming language? For instance, forward versus backward chaining, where forward might be additive and backward chaining would be subtractive. Does that make sense, or is that the wrong way to think about it?
I like that analogy. I think I definitely think in terms of search order, and like when I write a logic program, I kind of think about, okay, this feels like it's kind of doing the forward chaining part versus like this feels like it's kind of reasoning backwards from an existing possibility space. But I mean, fundamentally, it's not doing that because it's all translating it to a Boolean expression and then throwing it to a SAT solver. So it's like kind of a white lie to like think about ASP in those terms, but I kind of do it anyway because that's how I'm used to thinking about logic programs. I do think, yeah, I think that kind of those ideas from logic programming do map fairly well into the additive versus subtractive distinction as well.
Okay, thank you. Does anyone else have questions? Oh, another one just popped up.
Yeah, yeah, the tools for exploring possibility spaces seem like they'd also be handy debugging tools for relational programming more generally. Yeah, I completely agree with that. I would love to have tools like this in all of the logic programming languages. That would be cool.
Basically, it comes up because I've been thinking about, when I've thought about tools for trying to debug why, miniKanren is slow to synthesize something. I sort of want to visualize the space of all of the things that it's considering.
Yeah.
In a very similar way. Even though, there are only partial solutions, I'm like, you're probably wanting to visualize the complete solutions.
Yeah. Yeah, I mean, if there are other tools, like, do you know, are there tools out there specifically for program synthesis or other applications that try to do similar things?
I don't know of any tools, just things that I have dreamed of.
Okay.
I have SAD tools that I've written myself.
I hope to chat with you more at some point. Sorry, say again?
I have SAD tools that I've written myself where I do printf style debugging of the iterative state as it's being constructed, and it's terrible. I would never I would never want anyone to use that, but that seems to be the best I have available.
Well, I would love to talk to anybody who wants to, if someone would like be willing to share their screen and walk me through a process of like, I'm trying, a synthesis problem you're working on where you're trying to figure out how to navigate the possibility space, that could be extremely useful for thinking about the sorts of tools to build for this kind of thing. Thanks. Oh, I see another question on the screen. Okay, for generate and test, would it be possible to show which lines eliminate the most possibilities? It should be. I mean, I think so. Generate and test is kind of a broad classification of like several different PCG techniques. So I think it really depends on the technique, but yes, in principle, it does seem like that would be possible and useful. I think about a little bit about like, it reminds me a bit of decision tree learning, in which you like try to construct a decision tree where the most differentiating decisions are closer to the root of the tree. Yeah, and so since that kind of thing is automatable, it seems like maybe something like that would be as well.
All right, thank you.
All right, I have one more question before we move on. So back when you asked the question about are there 2 answers or 3 answers, does answer set programming assume a closed world? Is that the reason why there are only 2 answers rather than 3?
Yes. So, so the question is, does answer-type programming assume a closed world? And essentially, yes, because it is doing this preliminary step of grounding out all of your rules. It then assumes that that's all, that's all folks, right? Like that's, and those are the only things that are possible. The way that you kind of add back in like a little bit of the functionality of an open world is with choice rules. You can kind of say this is a thing that like may or may not exist. But aside from those things that you explicitly permit to vary, it doesn't assume an open world.
Okay, we have one more from Michael.
Oh, cool. Oh, yeah. Do people use probabilistic programming? Yeah, so I know of some people who've tried, I think, kind of designing probabilistic programming tools for PCG. I haven't really, I don't believe I've seen any kind of in action or any that have been, like, I don't think I've seen people publishing in like games conferences about probabilistic techniques. I would like to. I think it seems promising. I would especially like a tool that would allow you to, and I don't know, I think like people mean different things by probabilistic programming. I think there are several different things that can mean. But I think like a version of that in which you're sort of declaratively describing your like the probability space that you want to create, or the probability distribution that you want to create, and then like sampling from that could be really effective. Because otherwise you're kind of just relying on the emergent probabilities of the like density of examples in your solution space that exist.
Sounds like Will should dust off ProbKanren.
Okay, so Chris, if you have more time after, do you want to head to the lounge and answer more questions, maybe? Yeah. So we'll go to the next talk. Maybe
Sounds
Lisa
good.
can
Thanks,
find. Yep. Thank you again, Chris. That was really good, amazing. I really enjoyed this talk.
Thank you.
Is Lucas.
Sorry, I'm just trying to get everything set up. Okay. I think that's good, so let me start the video.
Sandra, and I'm an undergraduate student at the University of Toronto, Mississauga.
Hello, everyone. My name is Malaika Zaidi, and I just graduated from the University of Toronto, Mississauga, and this is joint work with Lisa Zhang. Today, we will be talking about our work on implementing a minimal relational floating point arithmetic.
So we implemented 3 basic relations: comparisons, addition and subtraction, and multiplication and division. Before we begin discussing our implementation, however, let's review floating point numbers. Floating point numbers are like scientific notation. If we want to write down the surface area of the Earth, we can do it like this. Here we are showing 5 significant digits, so we say that the precision is 5. There's one non-zero digit before the decimal point, so we call this number normalized. And the exponent is used to control the position of this decimal point. The same value can be written down in this format, and this is just to show that we're using a base 10 expansion. More generally, this is how we present a real number x in our floating point system. Here, beta, p, and L and U are characterizations of the floating point system. These represent the base, precision, and the allowed range of the exponent, respectively. Here, the di's are natural numbers, and the exponent range, L and U, are discrete values. More specifically, they are integers.
In our implementation, we use the following settings. The precision is a global constant that can be between 2 and 16. For simplicity, we use rounding by chopping and do not allow denormalized numbers. We represent a number in our system as a list with 3 elements and taking inspiration from the IEEE standard: a sign bit, an exponent, and a mantissa. Here, the exponent and mantissa are represented as a base 2 little endian representation of natural numbers. We actually use Oleg Keselyov's Relational Natural Number Arithmetic Library as helpers. Now, because the exponent is an Oleg number and we want an exponent to range from -126 to 127, we force the exponent to contain no more than 8 bits to get a range from 0 to 255. Then we shift it down by subtracting 127 to get the range -126 to 127. Finally, the mantissa is also an Oleg number. However, we fix the length of the mantissa to be equal to the precision of the system. Here are a couple more examples of floating point numbers in our system. Now we will begin the main portion of our talk with the introduction of our system's comparison relations. We implement 3 binary comparison relations. So the first one is FP equals, which is quite straightforward. The relation succeeds when the signs, exponents, and mantissa of F1 and F2 are equal, as can see here. Note, we also allow positive and negative zeros to be equal. Then we have the relation FP less than, and this relation can actually succeed in several ways, each corresponding to a Kondi branch. For example, one way for F1 to be smaller than F2 is for F1 to be 0 and F2 to be positive. Our next relation is FP less than or equal to, and this relation makes use of the previous 2 relations as discussed. Now Lucas will give you a quick demo of the less than or equal to comparison relation.
Here's an example that uses the FP less than or equal to relation. Here we perform a query that searches for 5 numbers which are greater than 1. And here's just the representation for 1 in the system, and we are using 8 bits precision for this example. Let's run it. So as you can see, the query is resolved very quickly, and I'll just briefly go through the results. The first result is 1. That comes from the FP equality relation. The next result is infinity. This comes from the FP less than relation. And then results 4 and 5 are just in the interval from 1 to 2.
We're now going to move on to floating point addition and subtraction. Before we begin discussing our implementation, let's just review how floating point addition works. Let's take this example on the slide, which is in base 2 and the precision is 4. Our first step is to determine the smaller exponent, which is the second number. Then we need to rewrite that number by shifting the mantissa to match the larger exponent, like so. Now we just need to do simple addition by adding along the columns. And our last step is to truncate the result to ensure that precision is equal to 4, and hence this is our result. Lucas will be showing the implementation of the addition-subtraction relation, along with examples to show how the relation works.
Here is the code for FP plus O. The first thing we do is decompose our parameters, F1 and F2, our addends, and R, our sum, into their sign, exponent, and mantissa, respectively. Then we move on to separate it into 2 main cases, addition regarding 0 and infinity, and the more general case, which doesn't deal with 0 and infinity. In this case, we break it down into 3 main steps. Each step is done in its own relation. So FP plus O is responsible for rewriting the query so that all the addends and the sum have the same sign, either all positive and all negative. That's what this manipulation is happening right in these lines. Next, we'll move on to FP swapo. So here is FP swapo. FP swapo is responsible for ordering the exponents of the addends so that we treat the second parameter to have the largest exponent. This is an assumption that FP same sign add row, our next relation that we're going to talk about, uses to actually do the addition. So that's what these 2 branches here. They just compute the difference of the exponents and then determine which one is larger. So then going down to FP same sign add row, it follows the same steps as Malika just described, however they are out of order, and this is for performance reasons, which was determined experimentally by running tests over and over again. So that was our implementation for FP plus O, and now I'll show you a quick demo. In this example, I have prepared 2 queries which use FP plus O. The first query will compute the sum of 4 plus pi, and then the second query will compute 4 subtract pi. Let's run the first example. Here we go. The query resolves really quickly, and we get the expected result. Because we're using 8 bits of precision, pi gets rounded down to 3.125. That's about it for this example. Let's go on to subtraction. And subtraction is obtained by running fp plus o backwards. And here we go. As you can see, this query does take a little bit longer, but it's still resolved quickly. And another thing that's important to note here is that logic variables do appear in the mantissa. This is because you could assign those bits to either 0 or 1, and the relation will still hold.
Let's now move on to discuss floating point multiplication and division. But before we begin discussing our implementation, let's just review how floating point multiplication works. Let's take this example on the slide. It's a base 2 example where the precision is 3. So our first step is to determine the resulting sign by performing an XOR relation. So if two numbers that are being multiplied are positive, the product will also be positive. Then we need to multiply the two mantissas in a similar way to integer multiplication. Now we need to estimate the resulting exponent by adding the two exponents of the numbers. And now we need to normalize this number by ensuring that the decimal is placed after the leading 1. So the actual exponent will now be 3. Then we need to truncate the result to ensure that the precision is equal to 3, and this gives us our final result. Now, Lucas will be showing you our implementation.
Here is the code for fp multo. We first perform a decomposition on our 3 parameters, f1, f2, these are the multiplicand, and r the product. We decompose them into their sign, exponent, and mantissa respectively. We then branch into 2 main cases, a case to deal with special queries involving 0 and infinity, and the main driver for multiplication. This code follows the steps that Malika briefly just described. However, it is out of order. This is due for performance reasons. This ordering was determined experimentally by running tests over and over again. I will now show you a quick demo of using fp multo. Here's an example that we are prepared that will compute the product of 20 and 2, and it will compute the quotient of 20 divided by 2. Here is the representation for 2 and 20 in our system. Let's run it. As you can see, the query resolves quickly, and we get the expected result of 40. And 20 times 2 is 40. Moving on, we will now run fp multo backwards to perform division. This query will compute the division of 20 divided by 2. Not much else to say, let's run it. As you can see, this query also resolves very quickly, and we get the expected result of 10. 20 divided by 2 is 10. Let's explore how fp multo performs by squaring a couple numbers. The first number that we'll square is 0.001. Let's run it. As you can see, this query resolves very quickly. Let's just check out the next number, 0.05. This one's taking a bit longer. A lot longer. So this one took about 9.5 seconds to resolve. Right now you might be thinking that, oh, 0.05 is larger than 0.001, so maybe fp multo is just slow with computing when working with larger numbers. Let's test this hypothesis by squaring 63. This one's fast again. So the hypothesis was wrong. What happens when we square an even larger number, like 32,888? It's taking longer again. So this one took about 3.5 seconds to resolve. Can you see the connection between these examples? It's the mantissa. Here you can see a plot of FP Multi's performance against the number of non-leading ones in the mantissa. The fastest queries were 0.001 squared and 63 squared. These queries are fast because they have an easy mantissa for FP Multi to work with. 0.001 has a small number of ones, and they're all evenly spread out. So that would correspond to this section in the graph right here. 63 has all of its ones located in the most significant range of the mantissa. So, and there is about 5 of them. So that corresponds to this section right here, where the purple line is still basically on the x-axis in this graph. The slowest queries were 0.05 squared and 32,888 squared. 0.05 squared is slow because of the number of ones. If you paid attention, there was 7 ones in the mantissa, and they were evenly spread out. So that would correspond to about this section in the graph right here, and the data point would be right about here. 32,888 is slow because there are 4 ones concentrated on the least significant side of the mantissa, so that corresponds to this part in the blue, on the blue line right here, right as it starts to hit that exponential ramp up. So you can see that there's this exponential behavior when it comes to the number and the position of the ones in the mantissa. For our last section, we'll be discussing an interesting example. We will be exploring quadratic equations which determine the golden ratio. We will run these equations using precision values 5, 6, and 7 and observe the behavior. Let's get right into it. So here we are, where we've created a couple queries. Here is the first query. This is x squared is equal to x plus 1. Here we set y to be equal to x squared and equate it in FP plus O. Notice that there's this extra finite relation. This is because there's a variable on the left-hand side and the right-hand side of the equality sign. So if we substituted infinity for x, we would get infinity plus 1, which is equal to infinity, is equal to infinity squared, which is true because positive infinity squared is positive infinity. Moving on to the second form, we have x times x minus 1 is equal to 1. Here, I'm just performing a relational trick so that I don't have to define -1. And let's run it. Let's get the first value out. So, as you can see, these queries resolve relatively quickly. The first query, x squared is equal to x plus 1, took 2 seconds, while x times x minus 1 only took less than 1/5 of a second. Let's run it with precision value 6. So you might expect that these will take longer, which is the case. There is this exponential behavior when you increase the precision of the system. So here you can see that the x squared equals x plus 1 query took about twice as long as before, and the x times x minus 1 query took 1.5 seconds this time. Can anybody guess what happens when we bump up the precision to 7? Let's check it out. So, as you may expect, these queries will take longer. So we're just going to have to give this a minute. Not a whole minute. So, we actually won't wait for this next one to terminate, and that's because when the precision value is 7, there is no solution to x times x minus 1 equals 1. So this query would end up having to exhaust the entire search space to find that, so we're not going to wait for that. The reason why this doesn't have a solution is so any number that would be close to a solution, let's say x, if we multiply it by x minus 1, we won't get exactly 1. We'll get 1 with a couple bits set to 1 at the end of the mantissa, the least significant end of the mantissa, and this causes the results to be thrown out. Overall, we've just observed that even though that you are searching for the same value using equivalent equations, you can get varying behavior amongst the queries.
So to conclude, I wanted to talk about some learning points we had while working on this project. First, we found that ordering the conjects was not trivial. We tried many different orders, and it was just hard to predict what would and wouldn't work. Next, debugging was challenging. It's hard to tell why a relation is slow and what part is slow. We didn't know about GDisplay for a long time, and using it wasn't intuitive. Debugging relations in general is much harder than debugging functions. We also tried to drop the leading one to be consistent with the IEEE standard, but then quickly realized that it made things way too slow. We also wanted to support denormalized numbers, but it requires the mantissa to have a change in length, which ends up increasing the search space. Thank you for your time.
We hope you learned a lot about floating point arithmetic and enjoyed our talk.
All right, thanks, Lucas. And I guess Malika's not here, so.
Yeah, sorry, my mic was muted. I'd just like to start with a correction about what we mentioned, GDisplay. We thought that it was part of miniKanren, but it was actually something that you, Greg, wrote for us. So it's just a goal constructor that allows you to use basically counters to count up how many times like a certain goal was actually executed during a particular query. And that's just all I want to say about that.
Yep, no problem. Okay, we have a question from Alexander.
Sure. No, we barred NaN from being a solution. Unless if you include infinity as NaN, but I'm thinking you're talking more about the QNANs and SNANs in like the more standard IEEE setup. Is that correct?
Yeah. And I was also curious, is there like negative infinity and positive infinity?
Yeah, there's a negative infinity, positive infinity, and plus and minus 0.
Okay.
Thank you for your question.
I'll paste the GitHub link as well.
Thank you. Any more questions? There's another one, I think, right? Or no, that was just the old notification. So have you guys tried to use a different representation of floating point? For example, using a ternary number. So we were relying on Kesselyov's Oleg numbers, which are base 2. So no, in short. But that would be something that's interesting to change the base of the floating point system.
Yeah, I'm just kind of curious, like, is miniKanren a good platform to test a different representation of floating points or real numbers? Because that would be very interesting.
Yeah, this is really, I think one of the reviewers pointed out the same, had the same question.
Several years ago, I think in 2015, I actually wrote a base 3 relational arithmetic, which was able to express a lot of what Oleg numbers could express without needing as many of the representational tricks used. It was more straightforward. So the intuition that I had was that ternary numbers may make it easier to reason about carries and such.
Mm-hmm.
What about performance?
I believe one of the reviewers said that they found that something with a base closer to E would be faster, and 3 is closer to E, so it would probably end up being faster.
Did you find anything, Greg, from your empirical? Yeah, go ahead.
All right, don't be shy with your questions.
Although we are kind of over time, so maybe we can just say a few things and then we can move to the lounge. Does that sound good? Greg?
Sorry.
All right, going once, going twice.
All right, so I guess we can have the rest of the questions in the
Lisa,
lounge.
do you want to come up here?
Yeah, thank you again, Lucas.
Thank you
And
for letting
Malika.
me be here.
Yeah, thank you for the talk.
All right.
Glad we have a relational floating point system now.
Yeah, I think this was an idea from the miniKanren workshop last year. Okay, so I'm trying to...
Looks like Lisa is in air meet limbo.
Oh, am I?
Trying to materialize on the stage now.
I thought I was already on the stage. Hi, can you hear me?
Well, I see the slides from earlier.
Okay, can you hear me? Can you hear me?
Oh, you do? Maybe I'm in air meet limbo.
Okay, Lucas can hear me. I don't know, and Alex can see me. I don't know if anyone else can hear me. I will. Okay, I see a thumbs up. So that's. Thank you for the thumbs up. Okay, so I just want to thank the presenters, the authors, and the attendees, especially the people that stayed to the end. Thank you for yet another successful miniKanren workshop. Also, just want to have like a special thank you to our program committee. We had really high quality reviews this year, and Greg and I are really new to well everything. So it was really great to have the expertise of the a very experienced group of people and the steering committee as well, especially Will and Jason Heeman. And I also want to thank, where did Greg go? I just also want to thank the ICFP organizers, Leo, Zoe, and especially Hanali, who has been working with us to resolve all the technical difficulties, and also our student volunteers in the workshop, Alex and Yana. So thank you. I think that's everything that I wanted to say. I wanted to check if Greg wants to say anything, but I assume no. I'm trying to think if I forgot anything, but yeah, thank you again, and we'll hopefully see you next year. I know that the steering committee will be looking for someone to run the workshop. So I guess let somebody like Will Bird know if you are interested in running the workshop next year. Okay, I think we can move to the lounge now. Now that Greg's back, we can all leave.
Yep, I'm back, just in time.
All right. So we'll end the session today, and we'll see you in the lounge. I think Chris Martin said that they'll be there as well. So hopefully we can carry on the conversation there. Bye.
Thank you, everyone.